Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Right now, a photon that left the first stars more than 13 billion years ago may be entering your eye. For that photon, no time has passed at all. Its emission and its arrival are stitched into one instant, and yet for us, it has carried the memory of the universe's long story. Across galaxies, past gravity's bends, stretched by the slow expansion of space, only to meet you here in this quiet moment. Tonight's gentle journey is about light, not just the glow on your bedside lamp or the shimmer of a candle flame, but the timeless messenger that threads history together. We'll follow a single photon across ages, from the opaque fog of the early universe to the clear transparency of recombination, through the silent dark ages, past the birth of the first stars, through the bending of gravity, and into the strange duality where waves and particles blur. Before we begin, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into light together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. If I were to ask you to think of light, you might first picture something utterly familiar. The golden edge of sunrise slipping past your curtains, the steady glow of a desk lamp, or the cold white gleam of your phone screen as it flickers awake in the morning. Light is woven into your day so tightly that it's almost invisible as a subject in itself. It guides your steps when you walk at night, softens the shadows of your room, glitters on the surface of a glass of water. We rarely pause to notice it, yet light is the medium through which we see almost everything else. It is the messenger that allows the world to present itself to us. And still, beneath its ordinary presence, light is profoundly strange. It does not age as we do. It does not slow down or rest. It is both a ripple spreading outward and a particle that arrives like a single knock at your door. It is the warmth on your skin and the colours in a rainbow, the signal in a fibre optic cable, and the shimmer of a star millions of light years away. We often think of light as a simple fact of life, but in truth it is one of the most astonishing actors in the universe. Consider how easily we accept its presence. You flick a switch and the bulb blooms. You open a window and the morning pours in. But each time this happens, you are participating in something woven into the fabric of reality itself. When that light touches your eye, it has travelled at a constant speed that no material object can ever match, a speed that anchors the structure of space and time. It has crossed the room instantly from your perspective, yet if you were somehow able to accompany it, there would be no crossing at all, only the timelessness of arrival. Perhaps you remember a time sitting by a window as the sun slowly set. The room cooled, shadows lengthened, and light shifted from bright white to soft amber, then finally to a dusky blue. All the while, beams of sunlight had been travelling across empty space for 8 minutes to reach you. In those minutes, the earth spun slightly. Your thoughts drifted. Perhaps you sipped tea or checked your phone. But for the photons, those little parcels of light, the journey from the sun to your window did not take 8 minutes. It did not take any time at all. Their emission and their arrival are stitched into one single instant. This is one of light's deepest mysteries. From its own impossible perspective, a photon never grows old. And yet, while light itself is timeless, it carries time within it. The colour of starlight reveals how fast the universe is stretching, how far away a galaxy lies, even what elements burn within its stars. Light is a perfect courier. It records without effort. Every photon is a tiny historian whispering of its origin. And the astonishing part is that you don't need a telescope to participate in this story. Even the glow of the screen in front of you, even the glimmer from a candle is the same phenomenon. A photon born, flying at the cosmic speed limit and ending its journey in your eyes. Think about the last time you stood outside at night and looked up. The stars that twinkled above were not there now, in any ordinary sense. Many of those photons left their stars hundreds, even thousands of years ago. Some departed when ancient civilizations were just beginning to write on clay tablets. They have been travelling ever since, unhindered, until they landed softly in your gaze. What you saw was not the star as it is in this moment, but as it was long ago. To look into the night sky is to look into the past. Light is the bridge that makes such time travel ordinary, available to anyone with eyes to see, and yet we rarely stop to consider that miracle. Perhaps it is because light never demands our attention. It does not clamour or announce itself. It simply reveals everything else. It slips into our routines, illuminating faces and sidewalks, tracing the curve of a glass, catching on a raindrop, sketching a shadow against the wall. It is so constant, so reliable, that we forget it is even there. But once you do pause to notice, the strangeness becomes inescapable. You realise that this common presence, this everyday glow, is also the foundation of relativity, the canvas of cosmic history, and the quiet storyteller of the entire universe. So tonight, as we begin our long journey through the story of light, keep in mind that you are already bathed in its presence. It is not just an abstract subject in a physics book. It is on your pillow, across your floor, within your eyes. It connects you to the dawn 8 minutes away, to the stars thousands of years distant, and to the very first light of the universe itself. Light beside you, light within you, light across all of time. If there is one thing that makes light more mysterious than almost anything else in the universe, it is its relationship to time. Imagine a runner on a track. With each lap, seconds pass, the body tires, and eventually the race ends. Now imagine a different kind of traveller, one who never tires, never slows, and in some sense never experiences the race at all. That is what a photon is like. From the moment it is released, perhaps in the heart of a star or in the quiet glow of an atom, it sets out at the speed of light. And while we, sitting on the sidelines of the universe, measure its journey as taking minutes, years, or even billions of years, for the photon itself there is no journey in time. It is born and it arrives in a single unbroken instant. This is because, according to Einstein's theory of relativity, time behaves differently depending on how fast you move. For us, moving slowly compared to cosmic scales, seconds and minutes tick reliably on our clocks. For an astronaut travelling near the speed of light, those seconds would stretch, and an entire lifetime on Earth could pass in what feels like only a few years. And then, at the ultimate speed limit, light speed itself, time as we understand it simply stops flowing. Proper time, the kind of personal time that a traveller would carry with them, becomes zero. The photon accrues no age. There is no before, no after, only emission and then detection. Of course, we must add a small note of humility. Physics reminds us that there is no proper rest frame for a photon. In other words, we cannot truly place ourselves inside the experience of light, because the very equations that describe the universe break down if we try to imagine riding along at exactly that speed. And yet, the mathematics shows us enough to glimpse the outline of this truth. Light is timeless, and in that timelessness it becomes the perfect courier across the cosmos. Think of sunlight falling on your hand through a window. It left the surface of the sun about 8 minutes ago, travelled across 93 million miles of space, slipped past the tug of planets and the curve of Earth's atmosphere, and finally warmed your skin, You experience that as a small delay, the time it takes for light to cross the gap. But for the photons themselves, there was no delay at all. Their journey is stitched into one instant, no matter how far they travel. From the star's perspective, or rather from ours trying to imagine, they were born and arrived in the same breathless moment. And the same is true for starlight in the night sky. When you see a faint blue point from a distant galaxy, you're looking at photons that began their journey perhaps millions of years ago. Dinosaurs walked the Earth when some of those beams set out. Civilizations rose and fell while they crossed the void. Yet when they strike your eye tonight, they're as fresh as the instant they began. Light is a courier who never grows old, never carries the fatigue of distance, but delivers its message intact, across time and space. It is strange to realize that this quality of light means the universe is full of instantaneous bridges. Every photon that reaches us is not merely a messenger, but a window into the past. We do not see galaxies as they are, but as they were when their light left them. To look far away is to look long ago, because light is the only thread that ties us to those unreachable places. The photon has carried a snapshot perfectly preserved across billions of years without itself experiencing any of those years. Einstein himself was captivated by this. As a young man working in the Swiss patent office, he would imagine what it would be like to chase after a beam of light. He pictured running alongside it, keeping pace, and wondered, would the wave stand still, frozen in place? This thought experiment was one of the seeds that eventually led him to formulate special relativity, the theory that reshaped our understanding of time and space. It all began with the strangeness of light and the realization that its constancy demanded a new way of thinking about reality. We might never sit down and imagine ourselves chasing photons on an afternoon walk, but the same strangeness surrounds us constantly. Every time a lamp flickers on, every time your phone screen glows, photons are racing toward you with this timeless quality. They may be ordinary to your eyes, but each one is a little piece of physics' most profound truth. It is worth pausing to reflect on what this timelessness means for the idea of memory. We tend to think of memory as fragile, fading with time. Photons, on the other hand, seem to be built as memory itself. Their colour, their wavelength, their tiny shifts, all record where they came from and what they passed along the way. A photon stretched by the expansion of space carries within it the record of that expansion. A photon bent by the gravity of a galaxy carries the fingerprint of that gravity. A photon absorbed and re-emitted by an atom carries the signature of that atom's energy levels. Each one is an archive, as if the universe has entrusted light to be its perfect librarian. And yet, it is a librarian without its own sense of time. The shelves of its memory are infinite, but the photon itself never opens a clock, never ticks a moment. It is the contrast between us and light that makes the story so poignant. We live inside time, marked by seconds and days and years. Light moves outside of it, preserving those very years for us to glimpse when it finally arrives. So the next time you notice sunlight spilling across the floor or the glint of headlights on a rainy street, take a moment to remember, those photons are not age travellers. They are timeless messengers, carrying snapshots of their origins, arriving fresh no matter how far they have come. Light beside you is ordinary enough to read a page by, but extraordinary enough to whisper of the timelessness that underlies the entire cosmos. To understand light fully, we have to travel far back, so far that no stars existed yet, no galaxies, no planets, not even the cool, quiet atoms we know today. The universe in its earliest ages was a very different place. Picture a space not dark but blazing, filled with an ocean of particles, every one of them hot and restless. Photons were certainly present then, but they were not free in the way we think of them now. Instead, they were caught in an endless crowd, colliding, scattering, bouncing from one particle to another like dancers in a frantic ballroom where no one could find a clear path to the door. In those first hundreds of thousands of years, the cosmos was more like a blinding fog. You might imagine standing in the densest mist you have ever encountered on Earth, perhaps on a cold morning when clouds have settled close to the ground. Now multiply that by unimaginable brightness, and fill the air not with water droplets but with charged particles, electrons and protons too hot to join together into atoms. In such a storm, light could not travel far at all. Every attempt to move forward ended in another collision, another scatter, another delay. Photons did not stream. They jittered and ricocheted in all directions. This state is what physicists call a plasma, a soup of particles where electrons and nuclei are separated, unable to settle into the calm of atoms. In a plasma, electric charges wander freely, and light interacts with them constantly. To the photon, the universe was like an endless maze of mirrors, each step forward blocked by another reflection. There was no transparency, no open sky, no way for light to escape. If we'd been able to exist then and somehow open our eyes, we would not have seen galaxies or stars. We would have been blinded by the sheer glare of the plasma itself, unable to see beyond the nearest scatter. But the universe does not stand still. As it expanded, it also cooled, just as steam cools into mist and mist settles into water. Over time, the temperature dropped enough that protons and electrons could finally clasp hands and form neutral hydrogen atoms. This moment, hundreds of thousands of years after the Big Bang, changed everything. The fog began to lift. The endless collisions slowed. The photons, once trapped, suddenly found the universe opening up before them. This change is called recombination, though the name can be a little misleading. There was no earlier combination of these particles. They had always been separate in the chaos of the hot plasma. But now, for the first time, they combined, and the effect was dramatic. Photons were no longer constantly bounced around by free electrons. Instead, they could move almost unhindered, gliding through space like birds finally released from a cage. Imagine being inside a room filled with smoke so thick that you cannot see your hand before your face. Then imagine a wind blowing the smoke away in an instant, leaving the air clear, the walls visible, the way open. That is what happened on the grandest possible scale. The universe went from opaque to transparent. The fog that had trapped light vanished, and suddenly the photons that had been waiting could set out on their journey. Many of those photons are still travelling today. We know them as the cosmic microwave background, the faint, cool afterglow that fills the universe in every direction. If you tune an old television to an empty channel, some of the static you see is from those very photons, still humming across the cosmos after nearly 14 billion years. They are relics, fossils made not of stone but of light, carrying the imprint of that first great clearing. To call them fossils is not an exaggeration. Just as ancient shells or bones in rock preserve a record of life long vanished, these photons preserve a record of the universe when it was only a few 100,000 years old, an infant compared to its present age. The tiny fluctuations in their glow, the small ripples in temperature and density, are like fingerprints of the earlier structures that would one day grow into galaxies, stars, and planets. Astronomers study these faint patterns with telescopes sensitive to microwaves, reading them the way a historian reads ancient manuscripts. In those patterns lies the first chapter of cosmic history that we can see with light itself. So in this early fog, and in the moment when the fog lifted, lies one of the most dramatic transformations in the story of light. Before, photons existed but were caged, unable to travel far, their messages muffled before they could be heard. After recombination, they became the first true messengers of the cosmos, free to carry information across unimaginable distances. It is a turning point. The moment the universe allowed light to become what it is today, a courier of memory, a bridge through time. It is humbling to think that the glow of your room right now, the light from your screen, and the sunlight pouring into your window are all part of this same lineage. They are kin to those first liberated photons. Without that early fog lifting, without the universe's expansion and cooling, there would be no transparent cosmos, no starlight to guide our eyes, no galaxies to map, no quiet photons to enter your gaze tonight. And so when we speak of the universe becoming transparent, we are speaking not only of a physical change, but of the beginning of visibility itself. Before that moment, the cosmos was hidden even from its own light. Afterward, it became a place where light could carry stories, where the future could unfold in brilliance, where a photon could set out on a journey that would take billions of years yet feel, to it, like no time at all. When the fog of the early universe lifted, something profound took place. The cosmos became visible, not to us, because we were billions of years from existing, but to itself. It was as if the stage lights had been turned on in a theatre that had been filled only with muffled sound and unseen movement. Suddenly, the photons were free. They streamed outward in every direction, no longer trapped by endless collisions with wandering electrons. For the first time, light could travel without being stopped at every step. That opening marked the dawn of cosmic transparency. This event, recombination, unfolded about 380,000 years after the Big Bang, which may sound like a long delay, but compared to the nearly 14 billion years that followed, it was only the blink of an eye. In human terms, if the universe's entire life were compressed into a single calendar year, recombination would occur before January's first week had ended. Everything else, stars, galaxies, planets, and you listening now, would come much later. But this early clearing was essential. Without it, the universe would have remained a blinding plasma, with no way for structures to grow or for future observers to ever glimpse the past. The light released in that moment is still here. We call it the cosmic microwave background, or CMB. Imagine a faint, persistent afterglow filling the entire sky, stretched now into long microwaves by the expansion of space. You cannot see it with your eyes, but it washes over you at all times, invisible and gentle, like a ghostly warmth left from a fire long extinguished. When scientists first detected it in the 1960s, they thought at first their radio antenna might simply be covered with pigeon droppings. But no amount of cleaning removed the signal. It was everywhere, uniform, whispering the same ancient message from every patch of the sky. What they had stumbled upon was the fossil light of the universe, a direct remnant from the moment transparency began. If you could step into a time machine and arrive just before recombination, you would be blinded. The haze of free electrons would scatter every photon in all directions, but a tiny moment later, when those electrons joined with protons to make neutral hydrogen, the blinding glare would vanish into clarity. It would be like standing on a mountaintop as a storm suddenly clears, the clouds tearing open to reveal blue sky. The light does not vanish. Instead, it streams freely. And what is extraordinary is that this light did not fade away over the ages. It expanded, cooled, and stretched. But it remains here now, waiting patiently for us to notice. Astronomers use satellites like COBE, WMAP, and Planck to measure this glow with exquisite precision. They see not just a uniform wash of light, but tiny ripples, minute fluctuations in temperature and density. These ripples are the seeds of everything to come: galaxies, clusters, filaments, the very cosmic web. They are written into the CMB like faint brushstrokes on the oldest canvas in existence. When you look at a map of the cosmic microwave background, you are looking at a portrait of the universe as a baby, still swaddled in its first blanket of light. There is something profoundly moving in realizing that this ancient glow still touches us. The photons have travelled across all of time, carrying the conditions of that early universe to our detectors and our understanding. They are not echoes in the sense of sound fading into silence. They are survivors, still vibrant, still faithfully telling the story of their birth. Every telescope tuned to the right frequency is a kind of ear pressed against the cradle of the cosmos, listening to its first cry. In more ordinary terms, you might have brushed against this glow yourself without knowing. On old televisions, when channels were not tuned properly, the snowy static on the screen contained a fraction of that ancient light. In between the noise, you were glimpsing photons that had begun their journey nearly 14 billion years ago. It is almost comical to think that the universe's grand first message ended up mixed into the background hum of living rooms, flickering unnoticed while people adjusted rabbit ear antennas. Yet that is the nature of light, always present, rarely demanding attention, but filled with meaning when we pause to listen. This transition to transparency was more than a shift in the visibility of the universe. It was the beginning of history as we can study it. Before recombination, the cosmos leaves no direct light for us to detect. The plasma erased all memory of earlier moments, but with transparency, the record begins. From that point onward, photons are free to carry information across space, and we, much later, are free to catch them. In this sense, the cosmic microwave background is the universe's diary entry number 1, the first legible sentence in a book that continues to this day. And what a diary it is! By studying the CMB, scientists can measure the age of the universe, its composition of matter and energy, even hints about its geometry and ultimate fate. The details are intricate, written in the faintest of ink, but they are legible to careful eyes. It is as though the cosmos, in its very first clear breath, left us a note about itself, tucked safely into the light that has travelled ever since. So the first transparency is not only a physical event, it is also a philosophical one. It reminds us that clarity is not always immediate. Sometimes the most enduring stories emerge only after a long delay, when the fog lifts and the messengers are allowed to depart. Those photons set free in the universe's infancy are still gliding past you at this very moment, silent and timeless, carrying with them the first visible record of all that was to come. Once the universe became transparent, light was finally able to stretch its wings and travel freely, but the story did not immediately blossom into galaxies and stars. After recombination, after the great clearing of the cosmic fog, the cosmos entered what astronomers call the Dark Ages. The name may sound foreboding, but it is simply descriptive. The universe was filled with light, yes, but no new sources of light had yet been born. The first stars had not yet ignited. There were no galaxies glittering in clusters, no quasars blazing. Only hydrogen and helium gas filled the vastness, spread thin and cooling as space continued to expand. Imagine walking into a vast cathedral at night, its vaulted ceilings towering high above you, but with all the candles snuffed out. The architecture is there, the space is immense, but it is silent, unlit, waiting. That was the universe in this period. The photons released at recombination were streaming in every direction, carrying their record of the first clarity, but otherwise the cosmos was profoundly quiet. Those ancient photons were not idle. They continued their journeys, and as space expanded, their wavelengths stretched. What began as brilliant radiation slowly shifted to longer and longer hues, like the note of a violin being drawn out and deepened until it becomes a low hum. This is the phenomenon of cosmological redshift. As the very fabric of space expands, it pulls the waves of light along with it, stretching them thinner, lowering their energy. It is not that the photons are slowing down, they always move at light speed, but their song is lengthened, transformed by the growth of the cosmos itself. If you have ever stretched a rubber band, you know how the band grows thinner, the tension spreading out. Something similar happens to light in an expanding universe. Photons are not objects that can be stretched physically, but their wavelengths, the measure of their energy, are extended by the swelling of space. This means that the colour of ancient light encodes distance and age. The farther it has travelled, the more the universe has expanded during its flight, and the redder the light appears to us. In this way, every photon carries within it not just the message of where it came from, but also how much the universe has grown during its journey. During the Dark Ages, the photons we see today as the cosmic microwave background were gradually stretched into longer and cooler wavelengths. What once would have been more like a blinding glare is now a soft bath of microwaves. If you were somehow able to float in that young universe, the glow of recombination would have still surrounded you, but it would have grown fainter and redder with each passing eon. It was light still travelling, but muted, as though waiting for something new to accompany it. This quiet era lasted for hundreds of millions of years. It might sound empty, but in truth it was a time of preparation. Gravity was at work in the darkness, tugging gently on the clouds of hydrogen and helium, drawing them into denser clumps. The seeds of galaxies were forming silently, invisibly, while photons slid past. Light did not stop moving, but the universe had not yet lit its own lamps. In one sense, this age was like the long night before a festival. You know the morning will come, but for now everything is hushed. The decorations, the galaxies are not yet hung, the lanterns, the stars are not yet burning. The universe was vast and empty to the eye, but beneath the surface structure was gathering. The photons kept on their timeless march, unaging, unaffected, recording silently the growth of the stage around them. When we look back at this period with modern instruments, we cannot see it directly. There was little for light to reflect or illuminate. Instead, we infer its nature by studying the faint traces left in the CMB and by modelling how those first clumps of matter would have behaved under gravity's steady hand. It is a little like trying to reconstruct the silent hours before dawn by the way the morning dew settles on the grass. The details are faint, but the outlines are clear enough. The universe was in waiting, quiet but not idle, filled with photons gliding endlessly in a starless void. There is something haunting and beautiful about this idea. Light existed, yet the universe was dark. Messages were travelling, yet there was nothing new to send. It was a lull between cosmic chapters, a silence heavy with potential. For the photons themselves, of course, there was no waiting. They did not measure those hundreds of millions of years, because they do not measure time at all. They simply travelled, and by travelling, they carried the conditions of the universe forward. To them, the Dark Ages were no different than any other instant. And so this session of the story reminds us, sometimes light is not about brilliance or spectacle. Sometimes it is about persistence, the quiet continuation even when nothing seems to change. Photons streamed through the empty vastness, stretched thinner and thinner, waiting for the moment when the universe would spark its first stars into life. That moment would come soon enough, and when it did, the silence of the Dark Ages would give way to the music of starlight. After hundreds of millions of years of quiet, when the universe was filled with hydrogen and helium gas, but not yet with the sparkle of stars, gravity finally gathered enough matter together to ignite the cosmos's first true beacons. This moment was not sudden in human terms, it unfolded gradually over vast spans of time, but compared to the darkness that came before, it was as dramatic as striking a single match in a pitch-black cavern. The Dark Ages came to an end when the first stars were born. These pioneers of light were not like the gentle sun, you know. They were immense, far larger than our star, and burned with furious brightness. Made almost entirely of hydrogen and helium, they had none of the heavier elements that later generations of stars would inherit and use to form planets, oceans and living beings. They were raw, massive and short-lived. In only a few million years, an instant in cosmic terms, they burned through their fuel and collapsed, many exploding as supernovae. But while they lived, they shone fiercely enough to carve bubbles of clarity in the surrounding hydrogen fog. Astronomers call this epoch rayonization. The word might sound intimidating, but the picture is vivid and simple. Imagine the universe as a great field of mist, cool and quiet. Into that mist sparks flare, brilliant stars so powerful that their radiation tears apart the hydrogen atoms around them, splitting them back into protons and electrons. These bubbles of ionized gas expanded, like lanterns glowing in a dark fog, until eventually the bubbles overlapped and the universe became transparent once again, not just to the photons of the cosmic microwave background, but also to new starlight. The first lanterns of the cosmos did more than illuminate. They transformed the chemistry of the universe. When these giant stars ended their lives in spectacular explosions, they scattered heavier elements, carbon, oxygen, iron, into the surrounding space. These ingredients seeded the next generations of stars and eventually planets. Without those first stars, there would be no rocky worlds, no oceans, no bodies built of carbon, chains. The heavy atoms in your bones were forged in stars that descended from those very first giants. It is hard to picture just how extraordinary these first stars were. They may have been hundreds of times more massive than the Sun, radiating thousands of times more brightly. If you could stand on a world orbiting one, you would be bathed in a light so intense it would make our Sun seem like a candle. Yet you would not stand there long. Such stars were too unstable, too powerful to allow planets to settle around them. Their role was not to nurture, but to transform, to open the next chapter in the cosmic story. For the photons that had been freed earlier during recombination, this new era changed very little. They continued gliding along their ancient paths, largely unbothered by the first stars. Some would be absorbed or scattered, but most sailed on through the new bubbles of ionized gas, their journeys unaffected by the dramatic fireworks unfolding in galaxies yet unborn. The cosmic microwave background remained what it had always been, a vast sea of ancient light, stretched thinner and cooler by the expansion of space. But alongside that ancient glow, there was now something new, fresh starlight, born in the first nuclear furnaces of the cosmos. If the universe had been a silent stage lit only by a faint afterglow, now the actors had stepped on and lit their own torches. The darkness was broken not just by a scattered shimmer, but by blazing fire. When we peer deep into the cosmos with our most powerful telescopes, we try to catch faint whispers of this era. The Hubble Space Telescope, and now the James Webb Space Telescope, are tuned to detect the light of the earliest galaxies, stretched into the infrared by billions of years of redshift. What they see are tiny smudges, faint patches that might look unimpressive to the casual eye. But in truth, those smudges are ancient lanterns, the first gatherings of stars shining across 13 billion years to reach us. Each photon that arrives from those galaxies is a survivor of the earliest dawn, a messenger from the time when darkness ended. Think of what that means. Tonight, as you sit listening, photons may be entering your eyes that left their home when the very first stars were burning. To them, no time has passed. Their journey was instantaneous in their own frame. To you, they are stories delayed by billions of years, finally arriving. Light is not only a courier of physics, but of ancestry. It connects you to the first dawns, to the first chemistry, to the first lanterns that made your very existence possible. There is a poetic symmetry in this. The universe began in a blinding fireball, cooled into silence, and then, in the hush of the Dark Ages, gathered itself. Out of that quiet came the first sparks, the first true stars, burning so brilliantly that they reshaped everything. It is as though the cosmos needed a pause, a long breath in darkness, before exhaling into brilliance once, again. And in that exhale, the potential for everything we know was unlocked. So as you imagine the night sky, speckled with points of light, remember that beneath those familiar stars lies a hidden ancestry. The lamps that guide your eyes now are descended from those colossal, short-lived pioneers. Their light ended the Dark Ages, and their ashes seeded the worlds to come. We are, in the most literal sense, children of those first lanterns, built from the atoms they forged and scattered. Their brilliance was brief, but its echo is eternal. When the first stars had kindled and galaxies were beginning to take shape, photons were no longer travelling through an entirely empty canvas. The universe now had structure, vast clouds of gas, swirls of newborn galaxies, and the deep wells of gravity that such structures created. Light, as timeless and swift as it is, does not ignore gravity. Instead, it flows along curves that gravity draws into the fabric of space. Einstein's general theory of relativity tells us that gravity is not an invisible force tugging at objects from afar, as Newton once imagined, but rather the warping of space and time themselves. If you picture space as a vast, flexible sheet, then placing a mass upon it will dimple and stretch the sheet. The more massive the object, the deeper the indentation. When light passes through such a warped region, it does not take a straight path as we might expect in flat space. Instead, it follows the curve, bending gracefully as though drawn toward the mass. This bending of light is what we call gravitational lensing, and it is one of the universe's most elegant tricks. Consider a beam of light travelling from a distant galaxy. For billions of years, it has streamed silently across expanding space. Then, in the middle of its journey, it passes near another galaxy or cluster of galaxies. Their combined gravity bends the space around them, and the light, obedient to the geometry of space itself, curves along the distorted path. By the time it reaches us, the image of that distant galaxy may appear magnified, duplicated, or stretched into long arcs of brightness. Through this natural lens, astronomers can see objects far too faint to detect otherwise. In a sense, the universe has built its own telescopes, sculpted from gravity and light. On Earth, we use glass to bend and focus light in lenses. A pair of eyeglasses, a magnifying glass, or the curved mirrors of a telescope all work by redirecting light's path. Gravity achieves the same effect without any glass at all. The sheer presence of mass warps the stage, and photons, ever faithful, walk the curves that result. It is both strange and comforting to realize that the geometry of the cosmos itself is capable of focusing the ancient messages carried by light. The bending can be subtle or dramatic. When light grazes the edge of the sun, it is deflected by a tiny angle, enough that astronomers during an eclipse in 1919 were able to measure the effect and confirm Einstein's prediction. That observation, starlight bending around the sun's gravity, became one of the most famous proofs of general relativity. A century later, we can still imagine the wonder of those astronomers standing under the shadow of the moon, watching stars appear in places they should not have been, all because their light had been gently bent by the sun. But gravity's influence is not limited to gentle nudges. Around black holes, the warping becomes extreme. A black hole compresses so much mass into such a small region that the very fabric of space folds inward. Photons passing nearby are bent not by small angles, but by dizzying arcs, sometimes even looping around the black hole before escaping. At a certain distance, called the photon sphere, light can orbit the black hole in a precarious circle. This orbit is unstable. Any slight disturbance sends the photon spiralling inward to vanish or outward to escape. But it is an eerie possibility nonetheless, a racetrack of light around a darkness so complete that no light can cross its horizon. We cannot stand beside such a scene, but we can imagine it. A ring of brilliance, photons chasing one another around a silent abyss, circling endlessly until one misstep sends them away. And indeed, images of black holes captured by the Event Horizon Telescope show something like this. A glowing ring formed by light bent around the edge of the darkness, magnified by gravity into a halo that we can see from millions of light years away. For the photons that manage to escape, their paths are forever altered by these encounters. They do not complain, nor do they resist. They simply follow the geometry that space itself dictates. And when they reach us, they bring with them not just the image of where they began, but also the subtle record of the mass they encountered along the way. A bent beam tells us there was a galaxy here, a cluster there, a hidden presence of dark matter whose gravity shaped the path. Light is not only a messenger of where it started, but also of where it has travelled. Think of it like this. If you were to walk through a forest and your path curved around trees, streams and rocks, the shape of your footprints would tell another observer what obstacles had been present. In the same way, the bent pairs of photons tell astronomers about the invisible structures that populate the universe. Without gravitational lensing, dark matter would remain even more elusive, for it does not shine or absorb light. But by its gravity, it leaves fingerprints on the photons that pass by. And so, gravity becomes not an obstacle but a collaborator in the work of light. It reshapes the stage, and light faithfully performs the script. Together they create illusions that reveal truths, magnified galaxies, halos around black holes, the ghostly maps of invisible matter. The soft grip of gravity ensures that light never travels entirely untouched, and in those touches lie the secrets of the cosmos. For us, observing from our small planet, these distortions are gifts. They allow us to peer farther, to measure more, to glimpse the hidden architecture of the universe. When you see an image of a galaxy stretched into a delicate arc, you're seeing not only the light of that galaxy, but also the fingerprint of every mass along the way. It is a reminder that the universe does not simply allow photons to pass, it shapes their journeys, and by shaping them, it writes stories into their paths. So the next time you look at a picture of a black hole's glowing ring, or a galaxy cluster bending light into graceful curves, remember that you are not just looking at light as it left its source. You're looking at light as it lived its journey, bent by the soft grip of gravity, carrying with it not only its origin, but also every encounter along the way. By now, our lone photon has travelled far. It has slipped out of the fog of recombination, drifted across the silent dark ages, past the lanterns of the first stars, and even bent around the curves of gravity. But the journey is not through emptiness alone. The universe has grown into a sprawling network, a vast cosmic web of filaments and voids, galaxies strung together in clusters and sheets. And though most of this structure is invisible to the eye, light carries the record of its presence. Every photon that travels through the universe is brushed ever so gently by this hidden scaffolding. The marks are faint, but they accumulate into a story we can read. Astronomers often describe the universe as having a texture like lace or a sponge. Dense filaments of matter stretch across space, meeting at nodes where clusters of galaxies form, while in between lie immense voids, expanses so empty that they could hold thousands of galaxies and still be nearly vacant. If you could somehow step back far enough to see the entire structure, you would find that galaxies do not scatter randomly like grains of sand, but instead arrange themselves like the strands of an immense spider's web. This cosmic web is shaped primarily by dark matter, the unseen mass whose gravity draws ordinary matter into its framework. Now imagine our photons streaming through this web. It passes through filaments of hydrogen gas, across voids, and near clusters. Each time it interacts, however subtly, it acquires a signature. One of the most striking examples is known as the Lyman Alpha Forest, a poetic name for a rather technical phenomenon. As photons from a distant quasar, an ancient luminous galaxy core, travel toward us, they encounter clouds of neutral hydrogen gas along the way. Each cloud absorbs a very specific wavelength of light, one associated with the hydrogen atom structure. By the time the photon arrives at Earth, its spectrum is not smooth, but etched with countless little notches, like scratches on an old record. These notches, when studied, together resemble the trunks of a forest, each line a tree, each tree a sign of gas between us and the source. This forest is not a nuisance but a gift. Each notch tells astronomers about the density, temperature, and distribution of matter in the early universe. Together they form a map of the invisible structure, the filaments, the clusters, the very web itself. It is astonishing that by reading the scars left on a photon spectrum, we can infer the existence of entire structures we cannot otherwise see. Light, once again, proves itself not only a messenger of where it started, but also a witness to every step of its journey. You might compare it to a postcard that has been stamped and postmarked at every town along its route. By the time it reaches you, it carries not only the original message, but also a history of where it travelled. The photon is that postcard, its wavelength stamped by hydrogen clouds, its path curved by gravitational wells, its tone shifted by the expansion of space. When we analyse it carefully, we can reconstruct not just its birthplace, but the entire road it has taken. This is why light is often called the universe's historian. It does not simply arrive, it arrives annotated with marginal notes written by hydrogen, gravity, and time. The cosmic microwave background shows this vividly. Its ripples contain hints of the universe's early density fluctuations. Quasar light shows it again, etched with the Lyman alpha forest that reveals the growth of cosmic structure. Even ordinary starlight carries absorption lines that tell us about the elements in the star's atmosphere. Every photon is a record keeper, meticulous and silent. And beyond what we can see lies the hand of dark matter, guiding the cosmic web's formation. Dark matter does not emit or absorb light, but its gravity shapes the paths photons take. When light bends subtly on its journey, we can detect those bends and map the hidden mass. Gravitational lensing, even in its weakest forms, allows astronomers to sketch the outlines of invisible matter. In this way, light becomes the only tool we have to sense what cannot shine. It is like watching the ripples on a pond and deducing the shape of a stone hidden beneath the surface. If you pause and consider, there is something profoundly moving about this. We live on a small planet orbiting an ordinary star, yet we can know the arrangement of matter across billions of light years, all because photons carry faint signatures with them. The universe has no obligation to make itself knowable, and yet it does through light. It leaves records scattered in every spectrum, waiting for us to learn how to read them. The cosmic web itself is breathtaking to imagine. Vast filaments spanning hundreds of millions of light years, forming a skeleton upon which galaxies hang like beads on a string. Between those filaments are the great voids, silent expanses with almost nothing at all. Our own Milky Way is part of one such filament, bound to its neighbours by invisible strands of gravity. And the photons arriving in your eyes tonight have threaded their way through this web, carrying with them the story of its shape. Perhaps you have walked through a forest at twilight, noticing how the trunks stand in rows, how gaps open between them, how light filters through in shifting patterns. The Lyman alpha forest is something like that, though written not in wood and shadow but in hydrogen and wavelength. To us it may look abstract, lines on a graph, but to the photon it is simply the record of a journey. Each scratch, each line, is a reminder that the universe is not smooth, but textured, structured, alive with hidden architecture. So the next time you see an image of the cosmic web, those glowing simulations of filaments and voids, remember that our knowledge of it comes almost entirely from light. We have never touched those filaments, never set eyes directly upon dark matter, never crossed the yawning voids. Yet photons, tireless and timeless, have done all of this for us, and they have delivered their annotated diaries into our hands. The universe leaves its fingerprints on every beam of light, and by reading them, we begin to understand the grand design of everything. Long before there were telescopes or equations, before anyone could speak of photons or wavelengths, light was already central to the human imagination. It was too powerful, too essential, and too mysterious not to be noticed. For our distant ancestors, light was the great divider between safety and fear, between the warmth of day and the uncertainty of night. And because it was so fundamental, they wove it into their stories, their rituals, their very sense of what the universe meant. You can imagine a small community gathered around a fire tens of thousands of years ago. The flames crackled, sparks leapt upward, and the glow pushed back the surrounding darkness. For those early people, light was more than a physical phenomenon. It was life itself. The difference between being devoured by predators and feeling protected by the fire's circle. It is no surprise that when they looked up at the sun and the stars, they thought of light as sacred, as something beyond human reach. Many cultures imagined light as divine fire. In Greek mythology, Prometheus stole fire from the gods and gave it to humanity, a daring act that both empowered people and drew the wrath of Zeus. Fire was not just a tool, it was a symbol of knowledge and independence, something so powerful that the gods themselves had tried to keep it from mortal hands. The story captures the awe that light inspired, its ability to banish the dark, to warm, to cook, to forge. Fire was a gift that felt stolen from the heavens. In Egypt, the sun was Ra, the great god who sailed across the sky in a golden boat. Each day his light triumphed over darkness, and each night he journeyed through the underworld, battling chaos to return again at dawn. Light was not only illumination but order itself, the daily proof that the cosmos was reliable, that life could continue. To live was to bask in Ra's light, to trust in its eternal return. In Hindu tradition, light is celebrated during Duality, the festival of lamps. Here light becomes a symbol of the victory of good over evil, of knowledge over ignorance. Small flames placed in homes and streets are more than decoration. They are affirmations that light guides, protects, and redeems. A simple flame becomes a cosmic truth, reminding participants that even in the darkest times, the glow of understanding can prevail. The Norse imagined the world ending in Ragnarok, when the sun would be swallowed by a wolf, plunging everything into darkness before a new creation could arise. Here again, light is not passive, it is the very measure of existence. To lose the sun is to lose the world. The return of light would signal renewal. Even in more humble traditions, light was seen as eternal flame. The hearth fire was kept burning in homes and temples, tended carefully so that it would never go out. In Greece, the Vestal virgins guarded the sacred flame of Vesta, ensuring its continuity as a symbol of Rome's endurance. To extinguish the flame would be to threaten the community's very survival. What is striking in all these stories is that light was never regarded as ordinary. It was always bound up with creation, destruction, safety, knowledge, or divinity. And though we may smile now at gods sailing across the sky or wolves devouring the sun, the feeling behind these myths remains familiar. We too feel something extraordinary when we watch a sunrise paint the horizon in gold, or when we light a single candle in a dark room and watch how it transforms the space. In many ways, these myths were not wrong. They sensed something essential, that light is bound to life and to meaning. Without it, we cannot see. Without the sun's energy, we cannot eat, for plants would not grow. Without fire, our ancestors could not have cooked food or gathered safely. Light nourishes, reveals, warms, protects. It is no exaggeration to say that without light, there would be no culture, no history, no us. Think of how language itself reflects this reverence. We speak of enlightenment, of seeing the light, of illumination as a metaphor for understanding. We describe wisdom as brightness, ignorance as darkness. Even in our modern lives, bathed in electric glow, these metaphors persist. To find light is still to find meaning. What makes these myths especially poignant is how they anticipated truths that science would later confirm. They imagined light as divine fire, and indeed it is energy. They saw the sun as a god whose power sustained life, and indeed our very survival depends on solar radiation. They treated fire as a stolen treasure, and indeed mastery of fire transformed humanity. The myths clothed these truths in stories, but at their heart they recognized that light was no ordinary phenomenon. If you close your eyes now and picture what light means to you personally, you might think of dawn after a sleepless night, of lamps glowing in windows as you return home, of candles flickering on a birthday cake. These images, not so far from the myths of gods and heroes, they all point to the same intuition. Light is precious, it is life-giving, and it always carries more meaning than simple illumination. So before we dive into experiments and equations, it is worth pausing with these stories. They remind us that light is not only a scientific subject, but also a human one. Across cultures, across millennia, people looked up at the same sun and stars and saw in them something more than brightness. They saw fire stolen from the divine, gods sailing boats of flame, eternal lamps that must never be extinguished. They saw, in light, the essence of life itself. If myths gave light its divine aura, experiments gave it form and direction. Among the earliest and most profound of those experimenters was Ibn al-Haytham, a scholar living over 1,000 years ago in the golden age of the Islamic world. In the West, he's sometimes called Al-Hazan, but his legacy belongs to all of humanity. He asked questions about light not in the language of gods or symbols, but in the language of curiosity, careful observation, and quiet patience. Imagine a dimly lit room in Cairo around the year 1020. Heavy shutters block the sunlight, but in one wall there is a small hole, no bigger than the tip of a finger. Through this tiny opening, a beam of sunlight slips and strikes the opposite wall, casting a pale, round image of the outside world. It is the simplest form of what we now call the camera obscura, the dark chamber where light paints its picture. For Ibn al-Haytham, this was not magic, nor was it divine mystery. It was a clue, a way to see how light moved in straight lines, how it carried images with fidelity from the world outside to the wall within. He spent long hours with such chambers, experimenting with openings and angles, learning how images were formed. He discovered that if you made the hole smaller, the image grew sharper, though dimmer. If you enlarged it, the image grew brighter, but blurred. These were not the speculations of myth. They were testable, repeatable, demonstrable truths. Light was no longer only a sacred flame or a god's chariot. It was a physical phenomenon that could be guided, measured, and understood. At the time, many still believed in older theories of vision, including the idea that our eyes sent out beams that touched objects and brought back their image. Ibn al-Haytham was not satisfied with such explanations. He argued, carefully and logically, that vision came from light entering the eye, not emanating from it. He used experiments with mirrors, lenses, and darkened rooms to show how rays travelled in straight paths, how they reflected and refracted, and how they converged to form images on the eye. In doing so, he laid the foundation for modern optics. Picture him at his desk surrounded by manuscripts, lamps flickering, diagrams of rays drawn with meticulous care. He was not just a thinker, but an observer, insisting that truth must come from experiment rather than from tradition or authority. That insistence, that light itself should be the witness, was revolutionary. He's often called the father of modern optics, but his influence reached further. He helped shape the very idea of scientific method, that we must test, measure, repeat, and let the evidence guide us. There is a quiet beauty in the thought of this man in his darkened chamber, bending rays through pinholes and mirrors, watching how they behaved. He could not have imagined satellites measuring cosmic afterglows, or telescopes capturing galaxies billions of light years away. Yet, he began the same journey, asking how light moves, how it carries images, how it allows us to see. From his modest experiments flowed centuries of discovery, through Newton's prisms, Huygens' waves, Young's fringes, and on into the modern physics of photons and fields. It is worth remembering too that Ibn al-Haytham's work was not confined to light alone. He wrote about astronomy, mathematics, medicine, and philosophy. But light seemed to capture his imagination most deeply. Perhaps it was because light is the gateway to sight itself, the bridge between the external world and our inner understanding. In studying light, he was in some sense studying perception, truth, and knowledge itself. For us looking back across a millennium, his experiments may seem simple, almost childlike in their directness. A hole in a wall, a beam of light, an image cast on the other side. And yet, simplicity is often the seed of profound truths. Today, when you take a photograph with a digital camera, you're still working with the same principle. Light entering through an aperture, carrying an image onto a surface where it can be recorded. The technology has changed, but the principle is the same. The journey from Ibn al-Haytham's darkened chamber to the camera in your hand is long, but it is continuous. There is a deep continuity in this as well. That light, which had once been clothed in myth, could now be studied patiently in a quiet room. That a scholar in Cairo could see in it not divine fire but natural law, and that by doing so, he could bring humanity closer to understanding not only the world outside the window, but the workings of knowledge itself. So when we speak of Ibn al-Haytham's vision, we mean not only his experiments with light, but his vision of how truth is found. He trusted the testimony of photons more than the proclamations of tradition. He asked light to tell its own story, and he listened carefully. In that listening, the modern study of optics was born. From Ibn al-Haytham's careful experiments and darkened chambers, the story of light travelled onward into Europe, where new minds, new tools, and a new spirit of inquiry were reshaping science. The 17th century was an age of telescopes turned toward the heavens, of mathematics blossoming into calculus, of philosophy stretching into natural law. And in the heart of this awakening, light once again demanded attention. Was it a stream of tiny particles, or was it a spreading wave? The debate would echo for centuries, dividing great minds, each certain they had glimpsed the true essence of illumination. On one side stood Isaac Newton, a figure whose very name carries the weight of gravity, literally and figuratively. Newton was a master of mechanics, a thinker who could describe planets with equations and explain falling apples with the same precision. When he turned his attention to light, he saw sparks, particles, corpuscles as he called them. Light to him was a rain of tiny entities shot out from luminous bodies, travelling in straight lines and obeying laws much like the balls in his experiments of motion. He was convinced because such a model explained reflection and refraction neatly. Particles bouncing off a surface or slipping into glass at different angles could mimic what the eye observed. In the cool glow of a candle, Newton imagined not waves spreading outward, but a stream of tiny projectiles entering the eye. Picture him by candlelight, the great scholar hunched over a prism, watching sunlight split into colours. He studied how these colours bent differently, how each was refracted at a slightly distinct angle. To Newton, this reinforced his particle view, because each tiny corpuscle might be of a different size or property, giving rise to the spectrum of hues. With his authority and brilliance, the particle theory gained great weight. For decades, many followed his lead, accepting that light was a shower of minute sparks, obedient to the laws of mechanics. But not everyone agreed. Across Europe, another voice was rising, quieter but persistent. Christian Huygens, a Dutch physicist and mathematician, imagined something very different. For him, light was not sparks, but ripples. He thought of waves spreading across a pond when a stone is dropped, each point becoming a new source of ripples advancing smoothly outward. In his vision, light behaved like those waves, It moved not as discrete particles, but as an undulating front filling space with its rhythm. Huygens had reasons for his conviction. The way light spreads out when it passes through a small opening, the way it bends around edges and creates soft shadows, seemed more natural to describe with waves than with particles. Particles might fly straight, but waves naturally bend and interfere, softening and shaping the patterns they create. For Huygens, reflection and refraction could still be explained, but in the language of rippling wave fronts entering new media, slowing or speeding, changing angle just as sound waves bend when they pass from air into water. You can imagine him sketching carefully on parchment, arcs of waves spreading outward from every point, filling the page with graceful curves. His principle, that every point of a wavefront is itself the source of new spherical waves, remains one of the most elegant descriptions in physics. Though the mathematics of his time limited him, his vision reached forward into truths that would only be fully confirmed much later. So there they were, Newton with his sparks, Huygens with his ripples. Each camp explained some things well. Newton's corpuscles accounted elegantly for the straight-line paths of rays, for sharp shadows, for reflection and refraction. Huygens' waves accounted for bending and spreading, for soft edges, for patterns that particles struggle to explain. Both had evidence, both had logic, and both carried the authority of genius. For the scientific world, this debate was not merely academic. It was about the very nature of reality. Was light made of substance, of tiny particles that could be counted and weighed, or was it more ethereal, a disturbance in some medium, like vibrations travelling through the air? At the time, many leaned toward Newton, partly because of his towering reputation. If the man who explained the motions of planets and the pull of gravity said light was particles, who could argue? Yet Huygens' ideas lingered, waiting for experiments yet to come. Looking back now, it is tempting to see them as opposites, locked in contradiction. But in truth, they were each holding pieces of a puzzle too large for their century to assemble. Newton saw light's precision, its sharpness, its ability to travel in straight beams. Huygens saw its softness, its ability to bend, to spread, to interfere. They were both right in their own way, but it would take another 100 years and the careful fringes of an interference pattern to reveal how both sparks and ripples were part of the story. There is something almost poetic about this moment in history. Two great minds, each illuminated by candlelight, each bending over papers filled with equations and diagrams, each convinced that they were listening to light correctly. Newton imagined sparks leaping across space. Huygens imagined ripples flowing outward without end. Both listened intently, but light, as it so often does, kept its deeper secret quiet a little longer. And so, the debate stretched across decades, shaping experiments, inspiring arguments, fueling curiosity. Was light sparks, or was it ripples? The answer, as the world would eventually learn, was both, and yet also something stranger still. By the early 19th century, the debate between Newton's sparks and Huygens' ripples had lingered long enough that it felt almost like an inherited quarrel, passed from one generation of scientists to the next. Newton's immense reputation had tilted most opinions toward the particle view, but questions remained, and the curious minds of the new century were not willing to let them rest. If light truly behaved as particles, its path should always be sharp and predictable. But if light were a wave, then, under the right circumstances, it should reveal itself by creating patterns of interference, ripples colliding, overlapping, and forming fringes of brightness and darkness. It was in this atmosphere that Thomas Young, a quiet English physician and polymath, devised an experiment that would shift the argument in a way that even Newton's reputation could not resist. The double-slit experiment, as it came to be known, was almost disarmingly simple. Young allowed a beam of light to pass through two narrow openings placed side by side, then observed the pattern it cast on a screen beyond. If light were composed of particles alone, two bright patches should have appeared, like two small windows casting two beams. But that was not what Young saw. Instead, the light formed a delicate sequence of bright and dark bands, fringes arranged like rungs on a ladder, extending outward in a gentle rhythm. This was unmistakably the mark of interference, a pattern created when waves overlap, bright where crests reinforce crests, dark where crests cancel troughs. Young's fringes were, in their own quiet way, revolutionary. They showed that light could not be explained by straight-flying corpuscles alone. Something about it spread, bent and overlapped like ripples on water. To many, this was the proof Huygens had long awaited, the vindication of waves over particles. The beauty of the experiment lay in its clarity. No complex machinery, no elaborate mathematics, just light, two slits, and a screen. A child could understand the setup, and yet the conclusion was profound enough to unsettle centuries of thought. And yet, as is often the case, the story was not finished. The wave theory gained strength, explaining diffraction, interference, and the gentle fringes Young had revealed. But as physics advanced into the 20th century, other experiments began to show that particles had not been banished from the tail. When detectors were sensitive enough to register light as tiny packets, photons, they revealed that each click, each arrival, was like a grain, a particle. The paradox was inescapable. Send light through the slits one photon at a time, and still, slowly, patiently, the interference fringes would build. The pattern remained, even though the photons seemed to arrive individually. It was as if each photon travelled alone, yet carried within it the potential to act as a wave, interfering with paths it could have taken. Only when watched, only when a detector forced the question of which slit did you pass through, did the fringes vanish. Measurement, it seemed, collapsed the possibilities into a single outcome, erasing the delicate interference. Without our gaze, light was both crowd and loner, both whispering wave and solitary traveller. With our gaze, it chose one role, as though the act of looking itself compelled light to take a side. Imagine the strangeness of this. You sit in a darkened lab, counting the faint clicks of a detector as photons arrive one by one, each as a solitary event, a speck of brightness. But as you gather more and more, a pattern begins to emerge, not random, but structured, fringes of light and dark spreading outward like the shadows of invisible ripples. It is as if each photon knows the experiment in advance, as if it senses the presence of both slits and adjusts accordingly, even though no one is there to guide it. For scientists, this duality was unsettling but unavoidable. Light was not merely particles, nor was it merely waves. It was both, and it was neither. It behaved as a wave when left unobserved, as a particle when detected. The truth was not in choosing sides, but in accepting that reality at the smallest scales did not conform to human categories. Light, it seemed, had written its own rules, and those rules demanded a new kind of physics, quantum physics, that would stretch imagination as surely as it stretched equations. To us, listening centuries later, there is something gentle in the way the story unfolds. First, the myths clothed light in divinity. Then Newton and Huygens, each certain, pulled in opposite directions. And then, with Young's fringes, the truth slipped out softly, not with thunder but with delicate bands of brightness on a screen. Proof came not with drama but with quiet repetition, as waves do, building until the pattern was undeniable. There is also something profoundly human in it. Newton at candlelight, Huygens sketching ripples, Young arranging slits in a board, all of them listening to light, asking it to reveal its nature. Each heard part of the truth, and each left the next generation closer to the whole. Today, when we speak of photons, of quantum mechanics, of wave-particle duality, We're standing on the quiet fringes that Young first revealed, still marvelling at what light whispered to him. So the double slit became not just an experiment, but a symbol. It reminds us that the universe is not obliged to fit neatly into our expectations. Light is both whispering crowd and solitary traveller, both ripple and spark, and perhaps that is why it has always fascinated us, from the fires of myth to the experiments of scholars, because light reflects the duality within ourselves, the need for clarity and the acceptance of mystery. By the middle of the 19th century, light was still an unsettled subject. The wave theory had triumphed in the eyes of many, especially after Young's interference fringes and later refinements, but questions lingered. What, after all, was waving? Sound waves moved through air. Water waves rippled across liquid. But light seemed to travel even through the void of space, without need of a medium. How could a wave exist in nothingness? Many still clung to the idea of a mysterious substance called the ether, an invisible fabric that filled the cosmos and allowed light to ripple through it. Yet this fabric had never been seen, never detected, never truly explained. It was a placeholder more than a solution. Into this uncertainty stepped James Clerk Maxwell, a Scottish physicist with a gift for seeing connections where others saw only fragments. He was not a flamboyant figure. He worked quietly, steadily, with a kind of patient elegance. But his vision changed everything. Maxwell looked at the scattered pieces of electricity and magnetism, fields of study that until then had seemed separate, and he began to sense they were in fact one story. Think of a compass needle twitching when near a magnet. Think of sparks leaping when you comb dry hair or walk across a carpet. Think of the way lightning forks across the sky, or the steady pull of a lodestone. To most, these were separate curiosities, electricity on one side, magnetism on the other. Maxwell, gathering the work of Faraday and others before him, wove them together into a single tapestry. He described how a changing electric field created a magnetic field, and a changing magnetic field in turn created an electric field. The interplay, this mutual dance, could sustain itself. One field giving birth to the other, rippling forward without end. And then came the realization, this self-propagating ripple was none other than light. Maxwell's equations predicted waves travelling at a speed that matched the measured speed of light itself. The revelation was astonishing. Light was not sparks, not ripples in a mysterious ether, but electromagnetic waves, disturbances in the fields of electricity and magnetism moving together through space. Imagine, if you will, the elegance of that discovery. For centuries, light had seemed almost magical, a mystery caught between sparks and waves, between divine fire and human experiment. Now Maxwell had given it a place in the order of physics, not as an isolated phenomenon but as a natural consequence of the fields already known. Light was the visible shimmer of electromagnetic fields in motion, the harmony of electricity and magnetism turned into a wave. You might picture him at his desk writing out equations that look, to the untrained eye, like cryptic symbols. But to Maxwell they were a kind of music, a score that described how the universe played its invisible instruments. He had composed a symphony of fields, and light was the melody that emerged. This is why many speak of Maxwell's work as one of the great unifications in science. Just as Newton had unified the falling apple with the orbiting moon, Maxwell unified static charges with glowing light. The everyday spark and the rainbow in the sky were revealed to be verses in the same song. For us, it is easy to take for granted. We flip a switch, and light fills the room. But hidden in that instant are fields entwined, creating and sustaining one another, rippling outward at 300,000 kilometers per second. When you hold a compass, when you see lightning, when you watch a rainbow, You are encountering pieces of the same story, pieces that Maxwell gathered into a single elegant whole. What makes this especially remarkable is how it freed light from the need of a medium. Waves on water require water. Sound requires air or some other substance to carry its vibrations. But electromagnetic waves require only space itself. The vacuum is not empty. It is a stage where fields can play out their dance. This realization quietly swept away the ether, even before experiments fully disproved it. The medium was unnecessary. Light did not need a carrier. It was its own carrier, a self-sustaining ripple of fields. Maxwell's insight was not just about light as we see it either. His equations described a whole spectrum of electromagnetic waves, from the slow undulations of radio to the furious crackle of gamma rays. Visible light was only a narrow band, a sliver between ultraviolet and infrared. Beyond what our eyes detect stretches a vast ocean of waves, all sharing the same nature. When you listen to the radio, heat soup in a microwave, or sit for an X-ray, you're still encountering light, just light of a different pitch, beyond the notes our eyes can play. It is difficult to overstate the impact of this unification. Without it, modern technology would be unimaginable. But even before its practical fruits, Maxwell's work reshaped our sense of beauty and science. There was a harmony here, a simplicity born of complexity, a set of equations that sang of unity. He had shown that light was not an exception, not a stubborn mystery, but part of a continuous story stretching across phenomena that once seemed unrelated. Perhaps there is something poetic too in thinking of equations as music. When musicians look at a score, they see more than dots and lines. They see rhythm, harmony, emotion waiting to be played. Maxwell looked at his equations and saw the same. A rhythm of fields, a harmony of forces, a melody of light. The cosmos, it turned out, was humming all along, and our vision was tuned to one small octave of its electromagnetic song. So in this session, we arrive at a moment of great clarity. Light is not divine fire, not tiny sparks, not ripples needing a mysterious ether. It is the self-sustaining dance of electric and magnetic fields, the melody of the universe written into its very structure. From the compass needle in your drawer to the rainbow arcing after a storm, from the warmth of a campfire to the glow of a distant star, all of it is Maxwell's symphony, playing endlessly across the stage of space. By the time Maxwell's symphony had been written and absorbed, it seemed to many that the story of light was finally settled. The elegance of electromagnetic waves was too convincing, too mathematically beautiful, to leave room for further doubt. Light, people thought, was a wave, nothing more, nothing less. The corpuscles of Newton had been set aside as a relic of history, and the triumph of waves seemed secure. And yet, as so often happens in science, nature had another surprise waiting. At the dawn of the 20th century, physicists were puzzled by a curious experiment involving metal plates and ultraviolet light. When light of a certain frequency shone upon the surface of a metal, electrons were ejected from it. This itself was not shocking. People already knew that light could impart energy. But what confounded them was the way this effect behaved. If light was purely a wave, then shining more intense light, even at a lower frequency, should eventually knock electrons loose. Waves carry energy in their amplitude after all. But experiments showed that no matter how bright the light was, if its frequency was below a certain threshold, nothing happened. It was as if the electrons were deaf to the volume of the wave and cared only about its pitch. On the other hand, even a dim beam of higher frequency light could instantly eject electrons, as though the energy was delivered in sharp, discrete punches rather than a gentle wash. It was a contradiction, and a stubborn one. Physicists tried to stretch wave theory to explain it, but the mismatch was too clear. The rules of waves alone could not account for the photoelectric effect. Enter Albert Einstein, at the time a relatively unknown patent clerk in Bern, with an imagination that refused to be confined by convention. In 1905, he proposed something radical. Perhaps light was not only a wave, but also came in discrete packets, tiny quanta of energy later called photons. Each packet carried energy proportional not to the wave's amplitude, but to its frequency. Shine a low-frequency light, no matter how bright, and each photon lacks the punch to free an electron. Shine a high-frequency light, even a faint one, and each photon is sharp enough to knock an electron loose. Suddenly, the photoelectric effect made perfect sense. This leap was unsettling. It meant that Newton's sparks had not been banished entirely. The particle picture, long dismissed, was back, though not in Newton's form. These were not hard balls flying through space, but quanta of energy, indivisible bundles that behaved in some ways like particles, in other ways like waves. Light, it turned out, was not content to sit on one side of the debate. It demanded both. Imagine Einstein pacing the narrow streets of Bern, thoughts racing faster than the trams rattling over cobblestones. He would later describe how he often carried images of thought experiments in his mind, riding alongside beams of light, watching clocks in motion. The photoelectric effect may not have been as poetic as chasing light across the sky, but it carried the same spirit of daring. To suggest that light was quantized was to challenge the prevailing wisdom of physics, to suggest that even Maxwell's elegant waves were not the whole story. The implications reached far beyond a laboratory curiosity. If light carried energy in discrete quanta, then matter might too. This idea would soon lead to the broader evolution of quantum mechanics, where particles and waves intertwined in ways that challenged common sense. But in 1905, it was enough for Einstein to show that the stubborn photoelectric effect could be explained if, and only if, light had a particle-like nature. It is easy for us now, living in a world filled with solar panels, photocells, and digital cameras, to forget how radical this was. Today we harness the photoelectric effect casually, turning sunlight into electricity on rooftops, converting photons into electronic signals in our phones and computers. Every time you take a photograph with a digital sensor, you're relying on the truth Einstein proposed. That light arrives in quanta, each one capable of nudging an electron free. What was once a puzzling contradiction has become an everyday convenience, woven into the fabric of modern life. But beneath the familiarity, the strangeness remains. A photon is not a wave spreading endlessly, nor is it a solid particle bouncing predictably. It is something else, something that straddles categories, a quantum entity that behaves like both and neither. The photoelectric effect forced physicists to accept that the world at its smallest scales was not built in the tidy shapes of classical mechanics. It was more fluid, more ambiguous, and far more mysterious. Einstein himself, though he proposed the photon, struggled with the deeper implications of quantum mechanics as it developed. He could accept that light came in quanta, but he resisted the idea that the universe at its foundation might be probabilistic, ruled by chance rather than certainty. Yet even his doubts could not halt the tide. The photon was here to stay, a central player in physics, as real as electrons and protons, and just as strange. There is something humbling in this story. Centuries of thought had swung between sparks and ripples, between particles and waves. Each camp had good reasons, each could explain some phenomena, and yet neither was complete. Then, with a simple experiment of light shining on metal, the universe revealed a deeper truth. It was not choosing between wave and particle, but insisting on both simultaneously. Light was not bound by our categories. It wrote its own. When you sit in sunlight and feel its warmth, when you turn on a lamp and see its glow, when you watch solar panels quietly generating power, you are living with the consequence of this discovery. Photons, those quanta of light, are touching matter, knocking electrons loose, and setting in motion the currents that power modern life. And yet, they're also waves, spreading, interfering, creating rainbows and fringes. Light remains even now the perfect paradox, both timeless courier and quantum spark. The photoelectric effect had returned, particles to the story of light, forcing physicists to accept photons as quanta of energy. Yet the wave theory had not disappeared, for interference fringes and diffraction patterns were still very real. Light was both at once, both ripple and packet. But how could this be? What did it mean for something to act as a wave until it was measured, and then suddenly to appear as a particle? To find answers, physicists returned to the double slit, the experiment that had unsettled Newton's corpuscles. What they found there would be stranger still. The classic version of the double slit involves shining light through two narrow openings and watching the resulting pattern. Waves made fringes, particles made two bright spots. When photons were sent one by one, the fringes remained, as if each photon had interfered with itself. But now, with more sensitive instruments, scientists could do something new. They could place detectors at the slits to determine which path each photon actually took. And that was when light revealed its most astonishing trick. The moment you watched, the fringes disappeared. With the detectors in place, photons no longer formed the wave-like interference pattern. Instead, they behaved like individual particles, each taking one slit or the other, each leaving its mark in a predictable line. Remove the detectors and the fringes returned, ghostly bands of brightness and darkness reappearing as though nothing had happened. It was as if light cared whether you were looking, as if the very act of measurement compelled it to choose a role. Of course, physicists are quick to say that light is not conscious, that it does not care in any human sense. But the language of performance is difficult to avoid. Light seemed to wait backstage, considering both roles, and then, when the curtain of observation was raised, it stepped forward as particle or wave depending on the script. Light waits for us to look, then writes its script, one might say, and though poetic, the phrase captures something real about quantum behaviour. Imagine going to a theatre where the actors rehearse both comedies and tragedies, and only when the audience takes its seat do they decide which play to perform. You cannot know beforehand. The outcome is not fixed until the curtain rises. That is what the quantum stage is like, and light is one of its most versatile actors. Physicists struggled and still struggle with what this means. Does the wave describe real ripples in space, or does it describe only probabilities, possibilities that collapse into certainty when measured? The Copenhagen interpretation, born in the early 20th century, suggested that the wave function is a description of potential, and that measurement forces reality to select one outcome. Others proposed hidden variables, unseen rules guiding photons behind the scenes. Still others argue that all outcomes occur, each in a different branch of a multiverse. Whatever the explanation, the fact remained. Light performed differently when measured than when left alone. This is not merely abstract. It has been tested, retested, and extended in countless variations. Photons sent through slits, electrons guided through crystals, even molecules large enough to be visible under microscopes, all show the same stage trick. Left unmeasured, they act like waves, spreading and interfering. Measured, they become localized particles. Reality seems to change its costume depending on how we look. For listeners in the calm of the night, it may feel unsettling, but there is also a strange comfort in it. Light has always been a messenger, carrying the history of the universe. Now it also carries a reminder that reality itself is subtler than our categories, that the boundaries between wave and particle, between possibility and fact, are not as rigid as we once believed. Think of rainbows, for example. To our eyes, they are simply arcs of colour, sunlight refracting through droplets. But on the quantum stage, each photon of that rainbow is a participant in this dual drama. It travels as a wave spreading across countless possible paths, yet it arrives as a single discrete particle, striking the retina in your eye and signalling the brain with precision. The rainbow is not just a pretty arc, it is a theatre of quantum decisions, each colour a chorus of photons rehearsing both possibilities until the moment of arrival. Or consider a dimly lit street at night, with an old lamp casting a pool of light on cobblestones. To you it is warm, continuous illumination. But in truth, the lamp is sending a flood of photons, each one a tiny actor choosing its role depending on whether it will be absorbed, reflected, or observed. The glow feels smooth, but beneath it is a quantum performance, each photon arriving with impeccable timing, never aging, always obeying the strange rules of its stage. It is tempting to imagine that light is playful, that it delights in ambiguity, but perhaps that is our way of humanizing the mystery. What matters is that in its behavior we see the limits of classical certainty. We learn that knowledge itself influences outcome, that the act of looking is not passive but participatory. Light has taught us that reality is not merely there to be observed, but is shaped, at least in part, by the conditions under which we observe. So this stage trick of light is more than a curiosity. It is a window into the quantum world, where possibilities blur, where certainty arrives only at the last moment, where particles and waves are different faces of the same phenomenon. For centuries, philosophers debated whether reality was made of substance or form, sparks or ripples. In the end, light reveals that it is both, and that the truth lies not in choosing sides, but in learning to live with the paradox. As we rest tonight in this gentle exploration, perhaps the lesson is not one of confusion, but of humility. Light does not fit into our neat boxes, and so it asks us to open those boxes, to allow for mystery, to accept that the universe is larger than our definitions. The photon, timeless traveller, perfect messenger, also turns out to be a trickster on the quantum stage, reminding us that reality itself may be a performance, ever shifting depending on how we choose to look. If light stage tricks at the double-slit unsettled scientists, its next revelation seemed even stranger. It is one thing for photons to behave as both waves and particles, another for them to shift their performance depending on whether we watch. But what happens when two photons become entangled, linked so deeply that they behave as one, no matter how far apart they are? This phenomenon, called quantum entanglement, shows us that light is not only a messenger but also a duet, a whisper carried across distances that defy ordinary understanding. Imagine two photons born together in a single event, like twins emerging from the same spark of energy. From that moment, their properties are tied. Measure one, and you immediately know something about the other, even if it has travelled far away. If one's polarization is found to be vertical, the other will be horizontal. If one's spin is this way, the others will be that way. They are coordinated, not by signals darting between them at faster than light speeds, but by the strange shared state in which they began. Einstein famously disliked this idea. He called it spooky action at a distance, a phrase that captures both his skepticism and his sense of wonder. To him, it seemed impossible that one photon could instantly affect another without anything passing between them. It violated his intuition about locality, the idea that objects are only influenced by their immediate surroundings. And yet, experiment after experiment has shown that the correlations are real. Entangled photons behave as if distance does not matter. Picture two lamps on opposite sides of a vast hall. They are lit at the same moment and their flickers are linked in perfect synchrony. No matter how far you separate them, even if you place one on Earth and the other on a distant star, their flickers remain coordinated. To the human imagination, it feels impossible, but to the quantum world, it is simply how things are. Of course, entanglement does not allow faster-than-light communication. You cannot use it to send a message instantly across the galaxy. The outcomes appear random until compared, and only when brought together do the correlations emerge. But the fact that they exist at all reveals something profound about light and about reality. Entanglement shows that separation is not as absolute as it seems. Two photons can be apart in space, yet still share a single description, as though they are one system stretched across distance. For many, this is difficult to accept. We like our world orderly, with objects here and there, causes before effects, and signals obeying the cosmic speed limit. Entanglement laughs at such neatness. It suggests that the universe is more holistic, more connected than we can see. Light, as entangled photons, becomes a kind of long-distance duet, each note harmonizing with the other even when played on opposite ends of the stage. Physicists have tested this again and again, using beams of entangled photons split by crystals and sent down different paths. They measure the properties at each end, compare results, and find correlations stronger than any classical explanation can allow. These tests, known as Bell experiments, confirm that the photons are indeed bound in ways no local hidden variables can explain. The verdict of nature is clear: entanglement is real. For us, listening quietly tonight, what matters is not the mathematics but the imagery. Think of twins finishing each other's sentences, no matter how far they are apart. Think of two dancers who learned a routine together and then, even when separated, move in harmony. Think of echoes that arrive not in sequence but simultaneously, as though the space between them has been folded. Entangled photons are not sending signals, they're sharing a single script. And this is not only philosophical. Entanglement is becoming part of our technology. Quantum computers use entangled states to perform calculations in ways classical bits cannot. Quantum cryptography uses entangled photons to create keys so secure that any attempt to eavesdrop disturbs the system and is immediately noticed. What once seemed like a mystical whisper is now the basis of practical, even revolutionary tools. There is also something deeply poetic in how this connects back to light's role as messenger. For billions of years, photons have travelled across the cosmos, carrying memories of stars, galaxies, and the early universe. Now we learn that pairs of them can also carry memories of one another, linked across any distance. They are not just couriers of places and times, but of relationships, of bonds that cannot be undone by separation. Perhaps that is why Einstein's phrase, spooky action, still resonates. It captures our sense that entanglement is not just a technical oddity, but a glimpse into the strangeness of reality itself. Light reveals that the universe is not entirely local, not entirely separate. Instead, it is woven together in ways we are only beginning to fathom. So when you look at a lamp, or a star, or the glow of your screen, remember that photons are not only streaming independently into your eyes. Some are born entangled, moving in pairs, carrying with them this uncanny connection. Though we cannot feel it directly, it is there, humming in the fabric of reality, a duet whispered across the void. And perhaps, as you drift toward rest, it is comforting to think that even light is never fully alone. It travels timelessly, yes, but sometimes it travels in harmony, bound to another across the great distances, carrying with it the quiet, reminder that connection endures even when space seems to intervene. When you think of light, you probably imagine what your eyes can see. The soft blue of the sky, the golden warmth of the sun, the deep red of a candle's flame, or the shifting green of northern lights. But this is only a narrow slice of something much greater. What we call visible light is like a single octave on a piano that stretches infinitely in both directions. There are notes too low and slow for us to hear, and notes too high and sharp for us to bear, but all belong to the same instrument. Light, in truth, is the entire electromagnetic spectrum, a vast continuum of waves and quanta, most of which pass silently through and around us, unnoticed by our eyes. At the long, slow end of this spectrum lies radio. Radio waves can be as long as buildings or mountains, undulating across kilometers of space. They are the deep ocean swells of the spectrum, slow and steady, invisible yet powerful. Each time you turn a dial and hear a song, or your phone connects to a tower, or astronomers map the faint hydrogen gas between galaxies, it is these enormous waves you're using. They wash through walls, travel across continents, and slip into the receivers of antennas both in city streets and on distant mountaintops. A little faster, with shorter crests, come microwaves. They are familiar to you not only because of the oven in your kitchen, humming softly as it warms soup, but also because they make up the very glow of the cosmic microwave background. These are the photons released when the universe first turned transparent, now stretched thin by expansion into microwaves that surround us constantly. Each time you heat leftovers, you're using the same portion of the spectrum that carries the universe's oldest light. The domestic and the cosmic share a single wavelength. Move upward in frequency again, and you arrive at infrared. Though you cannot see it, you can feel it. The warmth radiating from a fire, the gentle heat of the sun on your face, the lingering glow of a stone after sunset, all are infrared light. Animals such as snakes sense it directly, detecting the heat of prey in the darkness. Astronomers use infrared telescopes to peer through dust clouds that would otherwise hide newborn stars. In this range, light is not only vision but warmth, not only knowledge but comfort. Then finally comes the narrow band we call visible. This is the octave to which our eyes are tuned, the range our retinas can catch and translate into the colours of rainbows and sunsets. From red's long waves to violet's short tremors, we live our daily lives in this sliver of the spectrum. It is easy to forget how small it is, easy to mistake it for the whole. But just above violet lies ultraviolet, too sharp for our eyes, yet potent enough to burn skin. Bees and butterflies see in ultraviolet, finding patterns in flowers hidden from us, maps of nectar written in invisible ink. For them, the world is more richly painted than we can know. Above ultraviolet lie X-rays, familiar from visits to the dentist or the doctor. X-rays are the razor-edged whispers of the spectrum, able to pierce through skin and reveal bone, but they also stream from cosmic sources, exploding stars, black hole accretion disks, the furious hearts of galaxies. When astronomers build X-ray telescopes and send them above Earth's atmosphere, they see the universe not as a calm, starry sky, but as a battlefield of violent energy. At the very edge, beyond even X-rays, are gamma rays. These are the most energetic photons, born in nuclear reactions, radioactive decays, and the most cataclysmic cosmic events, collapsing stars, merging neutron stars, the birth of black holes. To our metaphors, gamma rays are not ocean swells or violin strings, but knife blades, thin and sharp, carrying energies that can transform atoms themselves. They remind us that light is not always gentle, that it can carry within it the power of destruction and transformation on cosmic scales. And yet, despite these differences in wavelength and energy, all are photons, all are light. The radio wave filling your room with music, the microwave warming your tea, the infrared glow you feel as warmth, the colours of a rainbow, the ultraviolet stripe on a butterfly's wing, the X-ray of a broken bone, the gamma ray burst from a distant galaxy. They're all the same phenomenon, the same electromagnetic ripple, differing only in frequency. The spectrum is continuous, a single instrument, though we perceive only a tiny fragment of its song. It is humbling to realise how narrow our eye's range is. If the entire electromagnetic spectrum stretched across a continent, visible light would be no more than a coin placed somewhere along the path. We live our lives illuminated by that coin, thinking it is everything, while around us the spectrum continues on endlessly in both directions. What we call darkness is often only light our eyes cannot see. The night sky, quiet and starry, hums with radio waves, bathes in infrared glow, and crackles with X-rays, even when it appears still to us. Technology has become our extended vision. Antennas catch radio waves, sensors feel infrared, detectors capture X-rays and gamma rays. With these instruments, we've opened new windows onto the universe, revealing a cosmos far stranger and more varied than visible light alone could ever suggest. Where once we saw only stars, we now see jets from black holes, dust-shrouded nurseries, the faint hydrogen tracing the skeleton of the cosmic web. The universe did not change when we built these detectors. It was always this way. We simply learned to listen to more notes in the symphony. So the next time you switch on a radio, warm food in a microwave, or glance at an X-ray, pause to remember that you are not just using technology, you are touching different keys of the same cosmic piano. The photon that tells your dentist about your teeth, the photon that left a distant galaxy billions of years ago, the photon that warms your hand by a fire. They are kin. They are notes of the same song, travelling at the same timeless pace, carrying within them the stories of where they came from. Light is more than our eyes can see. It is a spectrum of endless variety, a continuum of ripples and quanta, an invisible richness humming all around us. We live in its glow, warmed and guided by the small part we can perceive, but the rest continues, silent to our senses, waiting patiently for us to notice. Light is not only something that travels across the void of space, carrying the history of stars and galaxies. It is also something that greets us in every moment of daily life, not in silence but in dialogue with matter. Each time you look into a mirror, each time you watch a rainbow arc across a rainy sky, each time sunlight filters through a glass of water and scatters into dancing patterns on the table, you are witnessing a conversation. Light speaks, matter responds, and what you see is the outcome of their exchange. The simplest of these conversations is reflection. We take it for granted, glancing at ourselves in mirrors, admiring the gleam on a polished surface, or noticing the shimmer of light on still water. Yet reflection is remarkable. Photons meeting the surface of matter and bouncing away in a new direction, like polite visitors turning back at the door. In the right conditions, the reflection is sharp and faithful, preserving the details of the scene. A silvered mirror, for example, reflects with such fidelity that you can study the lines on your face or the patterns on a ceiling. In rougher conditions, waves on a lake, a brushed metal surface, the reflection is softer, distorted, as though light and matter negotiated but did not quite agree on the outcome. Refraction is another kind of conversation, a gentler bending of light as it passes from one medium to another. Dip a stick into water and it appears to bend at the surface. Place a straw in a glass and it seems broken into two pieces. This is light slowing as it moves from air into water, its path bending because it can no longer keep quite the same speed. In glass prisms, refraction separates white light into its spectrum of colours, each bent by a slightly different angle. Newton, with his prism experiments, demonstrated this vividly, showing that colour is not added by the glass but revealed by it. Every rainbow is nature repeating that experiment, raindrops acting as countless tiny prisms, each splitting sunlight into arcs of red, orange, yellow, green, blue, indigo, and violet. Scattering is subtler still. When sunlight streams through Earth's atmosphere, it meets molecules of nitrogen and oxygen. These molecules scatter the shorter, bluer wavelengths more than the longer, redder ones. The result is the sky itself, that vast blue dome that feels so ordinary yet is entirely the product of scattering. Without it, the sky would appear black even in daylight, as it does on the moon. At sunset, when sunlight travels through more atmosphere, the blue is scattered away, leaving the longer red and orange tones to paint the horizon. What we call the beauty of a sunset is, in truth, photons negotiating with air molecules, scattering differently as their journey lengthens. Then there are the shimmering puddles on hot roads, mirages created by refraction in layers of warm and cool air. Light bends gradually as it passes through air of changing density, making distant patches of sky appear on the ground like pools of water. Our eyes, accustomed to interpreting such light as reflection, insist there must be a puddle even when the asphalt is dry. It is light conversing with air, weaving illusions that fool us gently. Even the iridescence of soap bubbles or peacock feathers is another form of conversation, one involving interference, light waves reflecting off the different layers of a thin film overlap, reinforcing some colours while cancelling others. The result is shifting rainbows that change as you move, a delicate dance of wavelength and geometry. It is as though light and matter are composing music together, each colour a note struck by interference. In each of these cases, light does not travel blindly. It interacts, negotiates, adapts. Photons strike surfaces, bend in new media, scatter among particles, interfere in thin films. The outcomes are the phenomena we see: the blue of the sky, the curve of a rainbow, the shimmer of a bubble, the shine of a mirror. Light is not only messenger but also artist, painting the world in colours through its countless conversations with matter. There is poetry in this. When you stand in front of a mirror, you are not merely looking at yourself. You're seeing photons bounce from your face, strike silvered glass, and return faithfully to your eyes. When you watch a rainbow, you're watching the sun whisper to raindrops, each droplet splitting and sending its portion of colour toward you. When you watch the sky turn red at dusk, you are seeing photons scattered until only the longest hues remain, painting the air with fire as the day ends. And though we now explain these interactions with physics, with refraction indices and scattering cross-sections, the wonder is not diminished. If anything, it deepens. To know that the blue sky is light scattered by molecules no larger than a fraction of a wavelength is to glimpse the delicacy of nature's design. To know that rainbows are prisms of raindrops, each droplet turning sunlight into a fragment of a spectrum, is to appreciate the precision of light's artistry. To know that soap bubble iridescence comes from interference is to realise how even the thinnest film can become a canvas for the spectrum of creation. Perhaps the most beautiful way to say it is this: every colour we see is light negotiating with matter. Blue is the compromise of scattering, red is the persistence of long wavelengths surviving the atmosphere. Violet is the sharp bend of glass prisms. White is the sum of many conversations at once. Our eyes are the beneficiaries of these dialogues, interpreters of the silent language photons and atoms speak. So as you look around your room, notice how every glow, every shadow, every colour is born not of light alone, but of its interactions. The soft edge of lamplight on a wall, the sparkle of a glass, the sheen of polished wood, all are results of conversations carried out billions of times each second between photons and matter. It is a dialogue so constant we almost forget it, but once we listen, the world becomes more alive, more vivid, more filled with meaning. For all its resilience, for all its timelessness and swiftness, even light has boundaries it cannot cross. Photons may glide across billions of years, slip through cosmic webs, and bend obediently to gravity's gentle curves, but there are places in the universe where their journey ends. These are the realms of black holes, where the stage itself folds inward, and even the most faithful messenger of the cosmos falls silent. To imagine a black hole, begin with a star many times more massive than our sun. It burns furiously, fusing elements in its core until at last it can burn no more. Its own gravity overwhelms it, collapsing the star inward. The implosion is catastrophic, crushing matter into a point of infinite density, or at least into something so compressed that our physics can no longer describe it fully. Around this collapsed heart, space and time are drawn so steeply inward that nothing, not even light, can escape once it crosses the invisible threshold known as the event horizon. The event horizon is not a solid surface. There is no wall, no glowing boundary, only a region in space where the escape velocity exceeds the speed of light. For us, this limit is absolute. Nothing can move faster than light, not even light itself. And so, once a photon ventures too close and passes the horizon, it is lost forever to the outside universe. To those of us observing from afar, the event horizon is the ultimate silence, the place where even light cannot speak. But light does not vanish without leaving signs of its struggle. As photons approach the edge, they are stretched, slowed, redshifted by gravity. Imagine a violin string drawn out so far that its note drops lower and lower until it fades below hearing. That is what happens to light near the horizon. Its wavelength stretches into oblivion, its energy drained as if by an endless toll. To an observer at a distance, in falling light seems to freeze, never quite crossing the edge, fading slowly into darkness. The photon continues on in its own timeless way, but to us, it is swallowed. There is another strange boundary closer in, called the photon sphere. Here, light can orbit the black hole, circling round and round like a runner trapped on a track with no finish line. It is a precarious orbit, unstable and fleeting, but the very possibility is eerie. Imagine photons chasing one another endlessly around a circle, never escaping, never reaching us, until the slightest nudge sends them spiraling inward or flinging outward. This orbit leaves its mark in the glowing rings we now capture with telescopes, halos of light bent and magnified, forming the silhouette of the darkness beyond. The images of black holes taken by the Event Horizon Telescope, the glowing donut shapes that startle the world, are nothing less than light's last testimony. Photons emitted by hot gas swirling near the horizon were bent, curved and distorted until they reached our telescopes. Their paths carried the imprint of space so warped that geometry itself seemed to fold. What we see in those images is not the black hole itself, for that remains hidden, but the desperate orbiting of light around it, the ghostly ring of photons marking where silence begins. And yet, black holes are not only places of absence, they shape galaxies, fuel quasars, and anchor cosmic structures. Without them, the universe would not look as it does. Even in their silence, they play a central role, and light reveals their presence through its own distortions. When we see matter falling inward, glowing brighter as it heats, when we see jets of plasma shooting outward at nearly the speed of light, we're watching photons tell us about the invisible gravity wells that hold the stage together. There is something humbling, even a little haunting, in realizing that light, which has carried us so far through this story, meets its limit here. For billions of years it may travel across expanding space and through tangled webs, carrying notes from the earliest dawn. But if it strays too close to a black hole, it is gone, erased from the record, lost to us forever. The messenger is silenced, and no telescope, no matter how powerful, can recover its words. And yet, perhaps this silence has meaning too. It reminds us that the universe is not fully open to us, that some secrets remain hidden, not because we are not clever enough, but because the fabric of reality itself closes the curtain. There is dignity in that mystery, a reminder that knowledge has boundaries, that wonder survives in the spaces we cannot reach. Think of standing by the ocean at night. Waves crash beyond the dark horizon. Sounds reach you, but the water itself disappears into blackness. You know it continues, vast and endless, but your senses cannot follow. A black hole is like that horizon, a place beyond which light itself cannot carry the message back. And yet, we stand here, on the shore of space, listening to the waves that do reach us, grateful for the photons that survived. This is the darkest moment of our journey. Light, which has been our companion through myths, experiments, and cosmic travels, bows here to silence. But as always, the story does not end in shadow. Beyond black holes, photons continue to journey, continue to whisper across time. Their silence at the horizon makes their voices elsewhere all the more precious. For most of this journey, light has seemed like an independent traveller, slipping through fogs, weaving past stars, bending under gravity or vanishing into horizons. But for its story to reach us, there must be something waiting, some patient hand stretched out to catch it. That is where we humans enter. With our eyes, our instruments, our telescopes, we have learned to set nets for photons, to gather the ancient messengers and translate their silent arrivals into images, data, and understanding. Think first of the most basic net, your own eye. At the back of the retina lie millions of photoreceptor cells, each one waiting for photons to land. A single photon can trigger a response, starting a cascade of chemistry that becomes an electrical signal, then a perception. When you gaze at the night sky, you're already a telescope, catching photons that have travelled across centuries, carrying the shimmer of distant suns. Without instruments, without equations, the eye itself is a net for light, proof that biology has long relied on what physics only later came to describe. Yet the eye is small, limited. To catch the faintest whispers of light, humanity built larger nets. The first telescopes were modest, tubes of wood or brass, lenses polished carefully by hand. Galileo, peering through such glass, saw moons orbiting Jupiter and mountains on the moon. Discoveries made possible because his net was just wide enough to gather a few more photons than the naked eye. From then on, the history of astronomy has been a story of ever larger, ever more sensitive nets. On mountaintops across the world, domes of white or silver gleam under the sun, housing mirrors many meters wide. These mirrors do not create light, they only gather it. A faint photon that would have been lost in the sky instead strikes glass, reflects, and is directed to a detector. Multiply this by millions upon millions, and a dim galaxy, invisible to the eye, emerges from the noise. It is a patient craft. Astronomers waiting in the cold, instruments aligned, all so that a few more photons can be caught and their story heard. Consider the Hubble Space Telescope, floating in orbit above the blur of Earth's atmosphere. For decades, it has opened its aperture to the cosmos, gathering photons unblurred by air. In its famous deep field image, Hubble stared at what seemed to be an empty patch of sky, no larger than a grain of sand held at arm's length, and held its gaze for days. The result was astonishing. Thousands of galaxies revealed, each a swarm of photons arriving from billions of years in the past. Those photons had crossed nearly the whole age of the universe before ending their journey on Hubble's detectors. They had travelled timelessly, only to be caught at last in an artificial net built by human hands. Now consider the James Webb Space Telescope, its great golden mirrors unfolded like a flower in space. Webb is tuned to infrared, designed to catch photons stretched by expansion, photons that began their journey as visible or ultraviolet, but arrived cooled and reddened. These are the faintest messengers from the first galaxies, the earliest stars, the edge of cosmic dawn. To look at Webb's images is to hold in your hands the diaries of photons that left their homes more than 13 billion years ago, patiently crossing time to meet a mirror, a sensor, and finally your eyes. But not all nets are grand or in orbit. Some are simple antennas on Earth, stretched metal catching radio waves, translating them into signals. Others are arrays spread across deserts, listening to the low hum of hydrogen clouds. Each detector, no matter how small or vast, is a hand extended into the dark, waiting for photons, and always the photons arrive. They may come slowly, faintly, but they come, because light has never stopped moving since it was freed in the early universe. There is something profoundly human about this. Imagine an astronomer on a mountaintop, the air thin and cold, wrapped in a heavy coat. They wait in silence while above, the dome of the telescope rotates gently, following a star or a galaxy across the sky. The night is long, but their work is patience, to wait for photons to let them land one by one. When morning comes, the data is a collection of arrivals, faint traces of light caught after a journey unimaginably long. In those traces are galaxies, clusters, the curvature of space, the chemistry of stars. The astronomer has not travelled there, but the photons have, and by catching them, the astronomer listens. It is remarkable to realise that every picture of space you have ever seen is made of photons that have ended their journey in a net. The pillars of creation in the Eagle Nebula, the spiral arms of Andromeda, the glowing rings around a black hole. All of them are portraits drawn in photons that travel directly into our detectors. The universe is not shown to us by magic or imagination, but by light itself, arriving patiently until enough is gathered to reveal the image. Perhaps the most moving thought is this: photons have no proper time. For them, emission and absorption are stitched into one instant. A photon born in a galaxy 12 billion years ago did not experience those years. It was created, and then it was caught. Here, now. When you look at an image from Webb or Hubble, you are seeing a moment that to the photon was simultaneous with its origin. In some quiet way, telescopes collapse time, bringing the ancient and the present into a single shared instant. So, nets for photons are not only instruments, they are bridges. They connect us to stars and galaxies, to cosmic dawn and ancient afterglow. They make us participants in the universe's story, not merely observers but archivists, catching and recording the light that has been travelling since long before we were born. And the wonder is that the photons keep coming. They never grow old, never falter. All we need to do is hold out our nets, wait patiently, and let them arrive. When we look at light, we're not only seeing the present, we're always looking into the past. Every photon that enters your eye or a telescope is a messenger carrying with it the memory of where it came from. In this way, photons are not only couriers but historians, archivists of the cosmos who record events without ever aging themselves. They slip through expansion, through scattering, through gravity, yet they arrive unchanged in one essential respect. They carry the information of their origin. Each photon is a postcard from a distant moment in time. Consider the sunlight you see on your window each morning. Those photons were created in the core of the sun thousands of centuries ago, struggling their way through dense plasma until they finally escaped. By the time they reach you, they are perhaps 8 minutes old in transit from the sun's surface, but their deeper journey from creation has taken millennia. Every morning ray is both a note of the present day and a chronicle of processes long hidden within the star. Look further, and the effect grows more dramatic. The light of the nearest stars may have travelled years to reach us. The light of distant galaxies has travelled millions, even billions of years. When you gaze at the Andromeda galaxy on a clear night, the photons touching your retina began their journey more than 2 million years ago, long before our species walked the Earth. They crossed intergalactic space, bypassed wandering dust clouds, ignored the pull of intervening stars, and finally ended their journey by striking the fragile chemistry of your eye. In that instant, you become the final page of their story, the recipient of their ancient record. The further out we look, the deeper into history we see. Photons carry evidence of the universe's expansion, stretched in wavelength by the stretching of space itself. Redshift is not merely a technical term, it is the slow elongation of light's memory, the way photons mark the passage of cosmic time. A galaxy rushing away leaves its imprint on every photon, tinting them redder, longer, quieter in pitch. Measure this, and you measure the growth of the universe, the rate at which it expands, the geometry of space itself. Light does not only show us where things are, it shows us how they have moved and changed. Even the faintest photons hold treasures of information. The cosmic microwave background, released when the universe became transparent, is a bath of ancient light that has been travelling almost since the beginning. These photons are nearly 14 billion years old in our reckoning. They tell us about conditions when the cosmos was young, about temperature fluctuations that seeded galaxies, about density ripples that later grew into clusters. They are perhaps the oldest historians we can access, survivors of the early fog still carrying the signature of primordial times. Think of them as postcards stacked in layers. Some show the near present, sunlight, lamplight, the glow of fire. Others show the recent past, stars, nebulae, galaxies a few million light years away. Still others, faint and redshifted, show us billions of years back, when galaxies were just forming. And finally, at the edge of the stack are the cosmic background photons, faded but still legible, their handwriting telling of a time when atoms first gathered. The wonder is that we can read these postcards. By measuring the energy, wavelength, and direction of photons, scientists reconstruct the story of their origin. A photon stretched by redshift tells of expansion. A photon bent by lensing tells of a massive object between us and its source. A photon scattered carries the fingerprint of the medium it passed through. In this way, photons are not just passive couriers, they are witnesses, leaving clues of everything they have encountered. They are historians, not only of their birthplace but of their entire journey. For us, there is something almost tender in this thought. Light has been on the move since before there were humans to notice it, before there were planets to reflect it, before there were even stars to emit it. Some photons began their journey nearly as soon as there was space to travel through. They had no destination in mind, no audience promised, and yet billions of years later, they arrive in a telescope mirror or an eye on a small planet orbiting a modest star. To call this coincidence is perhaps too small a word. It feels more like an invitation, a reminder that the universe has been speaking all along, and only recently have we learned to listen. Every time we build a new detector, we widen the archive. Radio telescopes listen to ancient hydrogen. Infrared observatories pierce dust to see newborn stars. X-ray telescopes catch the fury of collapsed objects. Gamma-ray detectors register bursts from the edge of collapse and merger. Each photon adds a line to the story. Each measurement fills in a page. Slowly, patiently, the universe writes its history in light, and we, the latecomers, become its readers. And perhaps the most beautiful part is this. Photons themselves do not age. For them, emission and absorption are stitched together. No time passes between. To a photon, there is no gap between its birth and its capture. It carries its memory intact, as fresh at the end of the journey as at the beginning. The postcard never fades, never yellows with time. To us, it is billions of years old. To the photon, it is immediate. In that difference lies one of the quiet wonders of the cosmos. So the next time you look at starlight, remember you are not seeing the present. You're reading a history book written in photons, each line composed across unimaginable spans of time. The stars are not only shining, they're speaking, narrating their past, sending out messengers who arrive to whisper in your eyes the story of how they lived and how they changed. Light is the historian of the universe, and we are the audience fortunate enough to receive its endless archive. For so long in our journey, light has seemed limitless. It does not grow old, it does not tire, it slips through the cosmos across distances so immense that numbers falter. Yet light, for all its strangeness, lives by rules as strict as any law of nature. These limits do not diminish it. On the contrary, They are part of what makes it the perfect messenger, bound by constraints, yet universal in its behaviour, reliable across billions of years. The first and perhaps most profound limit is speed. Light moves at about 300,000 kilometers per second in a vacuum. To us, this is unimaginably fast, fast enough to circle Earth 7 times in a single second. Yet it is not infinite, and that finiteness gives the universe its sense of scale. If light were instantaneous, there would be no delay, no history written into distance. We would not look back in time when we looked at stars. We would see everything as it is now. The finite speed of a light is what allows the universe to have a visible past, to stretch out across space-time like a woven fabric of memory. This speed is not simply a feature, it is a limit written into the structure of reality itself. According to relativity, nothing with mass can ever reach it, and nothing can ever exceed it. The speed of light is the ultimate cosmic rule, a boundary drawn not by human convention, but by the very geometry of space and time. To accelerate any massive object toward that speed requires more and more energy, approaching infinity as you near the limit. Only massless particles, photons, gluons in theory, move at that exact pace. For them there is no option. A photon cannot slow down, cannot rest. Its very existence depends on perpetual motion. Think of it like this. For you, rest is possible. You can sit in a chair, you can sleep, you can be still. For a photon, rest is death. To stop moving would mean ceasing to exist, for the equations that describe light do not allow it to be stationary. This is a strange thought. A particle that is defined by its travel, a messenger whose only mode of being is movement. A photon exists only because it goes. Its journey is its essence. This leads to another limit. Because photons cannot rest, they cannot have a sense of now as we do. Proper time for a photon is always 0. From its perspective, if we dare use that word, emission and absorption are stitched together as one instant. There is no gap between beginning and end, no personal history of the voyage. For the photon there is no between. For us though, that between can be billions of years. The tension between these views, our slow unfolding of time and light's timeless crossing, is part of what gives photons their unique place in physics and in poetry. Another boundary emerges when light interacts with matter. It always travels at its cosmic speed in a vacuum, but in media, air, glass, water, it seems to slow. In truth, it is not the photon that slows, but its path that is interrupted, absorbed and re-emitted, bent and delayed as it converses with atoms. The effect, measured as refractive index, reminds us that even light must yield to the presence of matter. It cannot always rush unimpeded. It adapts, weaving through interactions delayed yet never destroyed. There are also cosmic horizons beyond which light cannot reach us. The universe is finite in age, and because light has a finite speed, we can only see as far as photons have had time to travel since the beginning. Beyond the cosmic horizon lies space we cannot access, regions whose light has not yet arrived. The speed of light gives us not only a limit of motion but a limit of knowledge. What we can see is bounded, a bubble defined by time and velocity. The rest of the universe may exist, but its photons have not yet spoken to us. Even black holes remind us of light's boundaries. The event horizon is not simply a place where matter disappears, but a region where the escape velocity exceeds light's maximum speed. No photon can escape once it crosses that threshold, not because it grows weak, but because space-time itself curves so steeply inward. The law of light's speed holds even here, and the consequence is silence. We might be tempted to see these limits as restrictions, but they are better seen as structures. They are the rules that make reality coherent. Imagine a universe where light had no limit, where it could move infinitely fast. Distances would collapse, cause and effect would blur, the very fabric of time would unravel. Or imagine if photons could rest. They would accumulate, pile up, clog the universe with stagnant light, and the story of energy and motion would vanish. What seems like restriction is in fact harmony, the conditions that make existence possible. There is something strangely comforting in this, that the universe has boundaries, that even the most ethereal phenomenon obeys laws. It means that when you look at a star, you can trust what you see. The redshift tells you its distance and velocity. The dimming tells you its age. The arrival time of its photons is not arbitrary, but bound by the cosmic speed limit. The rules give us reliability, a cosmos where messengers are faithful and predictable. And so we can say poetically that the speed of light is not only a number, but a sentence written into the universe. It is a promise that photons will always move at the same pace, that information will not travel faster, that the cosmic stage is ordered. This rule is everywhere, from the glow of a lamp to the edges of the observable cosmos. As you sit in this quiet moment, perhaps there is comfort in imagining that this rule applies equally to every photon, every beam, every glow. From the hum of radio waves to the searing sharpness of gamma rays, each obeys the same limit. Across time, across space, across all of history, the universe has one unbroken law: light moves at its speed and never otherwise. For all the grandeur of photons crossing billions of light years, for all the equations that describe their speed and their paradoxes, light is also the substance of our everyday existence. We live in it, grow in it, and measure our lives by its rhythms. To speak of light only as cosmic messenger would be incomplete. It is also the warmth on your skin, the timing of your body, the green in a leaf, the glow in a lamp. In every corner of life, light shapes us. Consider the plants outside your window or the food on your table. Their very existence depends on light. Through photosynthesis, green leaves capture photons, absorb their energy, and use it to bind carbon from the air into sugars. That single act underlies nearly all life on Earth. When you eat bread, when you sip tea, when you taste fruit, you're consuming the memory of sunlight stored in chemical bonds. Each bite is a translation of photons into nourishment. Without this quiet transaction, there would be no forests, no fields, no animals, no us. We often forget how delicate this balance is. A photon strikes a pigment molecule in a leaf, excites an electron, sets off a cascade of reactions that lead to the creation of glucose, which in turn fuels entire ecosystems. Billions of years of evolution honed this mechanism, so efficient that it turns sunlight into the breath you take. To live is to be, in a sense, condensed sunlight, matter rearranged by photons into the fragile architecture of cells and bodies. Light also sets the rhythm of our days. Our circadian clock, the cycle of waking and sleeping, of energy and rest, is tuned to light. Morning sunlight triggers chemical signals in our brains, reminding us to rise. Evening darkness allows melatonin to flow, preparing us for sleep. Even artificial light, when too bright at the wrong time, can disrupt this balance, keeping us awake when we should drift into rest. We are creatures of light not only in what we eat, but in how we measure time within our bodies. To step outside at dawn is not just to see the world illuminated, but to feel your own internal rhythm reset, like a watch winding itself anew. On a personal level, think of the moments that stay with you. Sitting by a window with the sun on your shoulders, walking under street lamps on a quiet evening, lighting candles for celebration or remembrance. Each is not simply about illumination. It is about meaning, about how photons shape mood, memory, and emotion. Light creates atmosphere, both literally and figuratively. A room bathed in soft golden glow feels warm, intimate. The same room under harsh white glare feels cold, impersonal. The photons are the same, but the arrangements change our experience. In art and culture, light has always been central. Painters layer pigments to capture its play on surfaces. Architects design spaces to harness or filter it. Musicians and poets invoke it as metaphor for clarity, hope, inspiration. Festivals around the world celebrate light in darkness, from lanterns floating in rivers to fireworks exploding in night skies. Across traditions, light marks joy, remembrance, transition. It is not only physical, it is symbolic, woven into our rituals of meaning. And yet, light is also deeply practical. Without it, vision would not exist. Our eyes evolved to detect a narrow band of the spectrum not by chance, but because this is the range where our sun shines most strongly and where Earth's atmosphere is most transparent. Vision is a gift of photons, tuned to our environment. Every book you read, every face you recognize, every landscape you admire is carried into your mind by streams of photons entering your eyes. Technology extends this gift further. Light fibers stretch across oceans, carrying conversations and data as pulses of laser photons. Traffic lights guide cities. Scanners in supermarkets read barcodes. Optical devices in medicine peer into the body. Everywhere we turn, light has been harnessed not only to reveal but to connect, to heal, to organize. In a way, our civilization is a choreography of photons. Solar panels turn sunlight into power. Fiber optics turn light into communication. Lamps extend day into night. Screens glow with stories, letters, and faces, bringing faraway voices close. When you look at your phone or your computer right now, you're watching patterns of photons dancing in precise arrangements, carrying thoughts from one mind to another. The same phenomenon that warmed the first leaves billions of years ago is now carrying the sentence into your eyes, and so we live in light at every level. It is cosmic, yes, but it is also cellular, cultural and personal. It grows our food, regulates our bodies, colours our world, powers our technology, and frames our rituals. Without it, the universe would still exist, but for us, there would be no life, no perception, no history, no meaning. Perhaps the most beautiful thought is that all these layers, leaf, lamp, poem, photon, are one story. The ray that left the sun may become sugar in a tree, warmth on your skin, or energy in a solar cell. It may be painted into art, refracted into rainbows, or woven into memory. It may whisper of galaxies or simply light your way home at night. Whatever the role, light is both the fabric of life and the fabric of meaning. So tonight, as you rest, notice the glow around you. The lamp at your bedside, the moon filtering through curtains, the faint shimmer of distant stars. All are parts of the same continuum, the same ancient current of photons. We live in light, and light lives in us, shaping every moment quietly, faithfully, endlessly. After wandering with photons across cosmic dawn, through myths and experiments, through equations and paradoxes, and finally into the daily warmth of our lives, it is time to close with a reflection. Light has crossed the universe, borne the signatures of stars and galaxies, revealed secrets through scattering and silence, carried paradoxes in its quantum whispers. And now, after billions of years, after distances we can scarcely imagine, some of those photons have arrived here, in this quiet moment with you. It is almost unfathomable to think about. A photon born in the core of a distant star began its journey before humans spoke, before Earth's continents looked as they do now, before our planet itself had taken its current form. It travelled across voids, past clusters, around curves of space, stretched by the expansion of the universe itself. To that photon, no time passed. Emission and absorption were stitched into a single instant. To us, its journey spanned billions of years, and somehow, improbably, it ended here, absorbed in the lens of a telescope or in the back of your eye, or as part of the glow on the screen you're looking at now. There is a kind of grace in that. Light does not choose where it lands. It spreads, it travels, it carries memory faithfully to whoever is listening. The fact that it meets us, tiny creatures on a small planet in a vast cosmos, is not necessity, but gift. We are not the intended audience, but we are an audience nonetheless, and in receiving light we become part of the story it tells. This makes the act of seeing, even something as simple as looking at the stars or noticing the lamp on your desk, feel like participation in a larger exchange. You're not just a spectator, but the final link in a chain that began long ago. The glow that reaches you is the completion of a journey that has crossed eternity. The message was written before there were readers, yet here you are holding it. In this way, photons are more than messengers. They are connections, tying us not only to the cosmos but to one another. When you light a candle, its glow may be modest, but it is photons radiating outward, perhaps reaching someone across the room, perhaps bouncing from wall to wall, perhaps even escaping into the night sky. That small flame links you to the people around you, and in a way, to the universe itself. This is why communities across the world have always gathered in light. Lantern festivals, bonfires, celebrations at dawn, vigils at night, each is a ritual of connection, a recognition that photons shared become bonds shared. Tonight, as you listen, you are part of such a ritual too. Around the world, others are listening, each in their own quiet space. Perhaps late at night, perhaps in the glow of a screen or the dimness of a lamp. And though you are separated by oceans and continents, you are linked by photons, arriving together across the globe. So I invite you, as always, to leave a note of where you're listening from and what time it is for you. These comments become like lanterns glowing in the dark scattered across the map of Earth. They remind us that though we are each in our own room, our own city, our own moment, we are connected by the same light, the same story, the same shared glow. There is something soothing in the thought that light has crossed billions of years only to arrive here tonight, just for this quiet instant. The universe is vast and time flows on, but this photon, this moment, this glow is yours. It is enough. And so as we close, may you carry that thought into rest, that light has crossed eternity only to meet you here, now. That its story is not only about galaxies and equations, but also about the warmth of your lamp, the rhythm of your body, the glow of your community. That to live is to live in light, and to rest is to rest in its gentle presence. May this quiet glow accompany you into sleep. And with that, we have finished tonight's journey. If you're still awake, I am glad you stayed. If you have already drifted off, that was the point all along. Light has carried us across the universe and back to this room. Sleep well, and may your dreams be gentle.